Right now, as you're sitting there, you're traveling through time. Your speed is about 1 second per second. Simple enough. But did you know you're also moving through space at an incredible speed? Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. Even if you're sitting perfectly still, the Earth is whipping you through the cosmos at tens of thousands of miles per hour. We treat where and when as two totally different things. They're the basic coordinates of our lives. Where are you going? When did that happen? One's a place, the other is a moment. It seems like the most obvious distinction in the world. But here's the thing. The universe doesn't see it that way. In fact, it has a strict, unbreakable law. The faster you rocket through space, the slower you must move through time. Why? Because space and time aren't separate at all. They're woven together into a single, four-dimensional fabric. And if you could somehow pull them apart, if you could treat where and when as truly independent, you wouldn't just be breaking some minor cosmic rule. You would shatter the very laws of reality. The pillars that hold our universe together, things like cause and effect, gravity, even the idea that energy can't just be created or destroyed, would all crumble into nonsense. Today, we're going to find out why. We'll see not just that space and time are linked, but why their union is the absolute bedrock of our existence. The intuitive lie we all believe. Before we can get our heads around the universe as it really is, we have to appreciate the universe as it seems. For thousands of years, our picture of reality was built on a simple, common-sense idea, an idea pretty much written into the rulebook by one of the greatest minds in history, Sir Isaac Newton. In the Newtonian world, space is the grand stage. Think of it as a giant, empty, three-dimensional box. It's absolute. It's fixed. It's the arena where everything happens. Every object has a precise spot inside this box. Here is here, there is there, and the distance between them is the same for everyone, no matter what. It's a rigid, unchanging grid. And then there's time. For Newton, time was like a universal river, flowing at the exact same rate for every person, every planet, and every star, everywhere. A second on Earth was a second on Mars and a second near a black hole. This cosmic clock just ticks along, completely separate from the stage of space. It's the great metronome of the universe, making sure that now is the same now for you, me, and some alien in the Andromeda galaxy. If two lightning bolts strike at the same time in London and Tokyo, Newton would say they struck at the same time for everyone, period. This worldview just feels right, doesn't it? It's how we live our lives. We have clocks on the wall and assume they're ticking away the same time as clocks across the globe. We use maps to measure distances, assuming those distances are concrete facts. Space is where, time is when, and they're as separate as up and down. This idea was the foundation of classical mechanics, the laws that let us send people to the moon and build bridges that don't fall down. For over 200 years, the separation of space and time wasn't just an assumption, it was the bedrock of physics. It worked so well, it seemed crazy to question it. But hiding in plain sight, within the laws of nature themselves, was a clue. A single, stubborn fact that just wouldn't fit. A fact that would eventually force us to tear down this whole comfortable picture and replace it with something far, far stranger. And that fact had everything to do with light. The cosmic speed limit and the crisis of physics. The story of how everything unraveled begins in the mid-1800s with another physics giant, James Clerk Maxwell. He was studying electricity and magnetism, and with four stunningly beautiful equations, he unified them into a single force, electromagnetism. But tucked away inside his own math was a bombshell. His equations predicted that a ripple in this electromagnetic field, what we call light, must travel at a very specific speed, just shy of 300,000 kilometers per second, or 186,000 miles per second. Now, that was weird enough. But the truly bizarre part was what the equations asterisk didn't say. They didn't say what this speed was relative to. Think about it. If you're on a train going 100 miles per hour and you throw a baseball forward at 50, someone on the ground sees the ball moving at 150 miles per hour. Speeds add up. That's common sense. So, physicists ask the obvious question: what is the speed of light measured relative to? The popular answer at the time was the ether, a hypothetical, invisible substance filling all of space that light waves were thought to travel through. The idea was that as the Earth orbits the Sun, it must be moving through this ether. So, if you measured the speed of light in the direction of Earth's motion, you should clock it as being a little faster. And if you measured it in the opposite direction, it should seem a little slower. Simple. This was a perfectly reasonable idea, and in 1887, two American scientists, Albert Michelson and Edward Morley, set out to prove it. They built an incredibly sensitive experiment to detect this ether wind. They expected to find that tiny difference in the speed of light. They found nothing. Absolutely nothing. The speed of light was the same. No matter which direction they pointed their machine, the answer was always 186,000 miles per second. This was a disaster. It was like throwing a baseball on a train and having someone on the ground see it moving at the exact same speed you do. It made zero sense. It broke the basic rules of addition we learn as kids. Physics was in crisis. For years, scientists tried to patch the theory. Maybe the Earth drags the ether along with it? Maybe the experiment's equipment shrinks in the direction of motion? These were desperate fixes for a theory that was clearly broken. The problem was a straight-up contradiction. You had Newton's laws of motion, which said speeds must add up. And you had Maxwell's laws, which said the speed of light is always the same. They couldn't both be right. The solution would require someone with the sheer audacity to suggest that maybe, just maybe, the speed of light is the one thing that's truly constant, and the things we thought were constant, space and time, are the things that have to bend. The union. A fabric called spacetime. In 1905, a young patent clerk in Switzerland named Albert Einstein published a paper that changed history. He took the bizarre result from the Michelson-Morley experiment not as a failure, but as a fact. Einstein started with two simple ideas. First, the laws of physics are the same for everyone who's not accelerating. Second, the revolutionary part. The speed of light in a vacuum is the same for every observer, no matter how fast they're moving. He just accepted the impossible as true and followed the logic. And it led him somewhere incredible. If the speed of light has to be the same for everyone, then something else has to give. And that something, Einstein realized, was space and time. Let's go back to that train. Someone on the train shines a flashlight from the floor to the ceiling. For them, the light travels a short, straight path. But now, picture someone on the ground watching this. They see the beam of light, but because the train is moving, the light doesn't just go up. It travels up and forward, along a longer, diagonal path. Here's the paradox. Both people must measure that light beam traveling at the exact same speed. But the person on the ground saw it travel a longer distance. If speed is distance divided by time, and they disagree on the distance but agree on the speed, then they must also disagree on the time it took. This was the bombshell. Time isn't absolute. From the perspective of the person on the ground, the clock on the moving train is literally ticking slower. This isn't some trick of the clock. It's a fundamental feature of reality. The faster you move through space, the slower you move through time. This is called asterisk time dilation. And it doesn't stop there. To keep the cosmic speed limit intact, space itself has to be flexible. An object moving at high speed will actually appear shorter in its direction of motion to someone standing still. This is asterisk length contraction. Einstein showed that space and time weren't the separate, rigid things Newton imagined. They were a dynamic duo, stretching and squeezing as needed to make sure the one true constant, the speed of light, was the same for everyone. But it was one of Einstein's old professors, Hermann Minkowski, who gave this idea its grandest form. In 1908, he declared, "Henceforth, space by itself, and time by itself, are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." Minkowski realized that Einstein was describing a four-dimensional structure. We don't live in a 3D universe that just happens to have time. We live in a 4D universe called asterisk spacetime. Your whole life isn't just a series of moments. It's a world line, a continuous path stretching through this 4D landscape. And here's the key. Everything in the universe is constantly moving through space-time at the speed of light. When you're sitting still, all of that motion is being used to travel through the time dimension. Your speed through space is 0, but your speed through time is maxed out 1 second per second. But the moment you start moving through space, you have to divert some of that motion away from the time dimension. You start trading speed through time for speed through space. The faster you fly through space, the less speed is left over for traveling through time. So, your time slows down relative to someone standing still. This is the heart of it. They're not independent. They're components of a single thing. You can't change your motion through one without it affecting your motion through the other. It's like walking northeast. You can't just decide to move north faster without it changing your eastward progress. Space and time are like that, inextricably linked in a fabric of space-time. But what would happen if we could actually rip that fabric apart? The shattered reality. This unified space-time isn't just a neat party trick. It's the foundation of everything. If you could pull space and time apart, what laws would shatter? The short answer is all of them. Reality as we know it would collapse. Let's look at the three biggest casualties. Law 1. Causality would disintegrate. The most basic rule of the universe is cause and effect. A glass shatters after you drop it. An effect can't happen before its cause. In Newton's world, the universal clock guaranteed this. But in relativity, there is no universal clock. So how does the universe keep the timeline straight? The answer is a concept called the asterisk light cone. Imagine a firecracker exploding. From that single point in space-time, light rushes out in all directions, forming an expanding sphere. On a space-time diagram, this traces a cone. This is the future light cone. It contains all the places and times that can possibly be affected by the explosion. Anything outside this cone is so far away that light from the explosion can't reach it yet. They are causally disconnected. This structure is what saves causality. For any two events where one causes the other, all observers, no matter how they're moving, will agree on the order they happened. But for events that are causally disconnected, something weird happens. Different observers can disagree on which one happened first. One person might see event X happen before event Y, while another, flying past, sees Y happen before X. This is the asterisk relativity of simultaneity. Does this break causality? No, because it doesn't matter who saw what first, since neither event could have caused the other anyway. The light cone is a sacred boundary. Now, imagine we could separate space and time. This would be like being able to travel sideways in space-time instantly. You could step outside your light cone. You could receive a reply to a message before you even sent it. A home run could be hit before the pitcher threw the ball. The universe would become a chaotic, illogical mess. The entire concept of A leads to B would be gone. Law 2. Gravity would cease to exist. For centuries, gravity was a mystery. Newton described what it did perfectly, but he had no idea how it worked. How does the sun pull on the Earth across 93 million miles of empty space? Einstein realized Newton's theory had a fatal flaw: it was instantaneous. If the sun vanished, Newton's laws said the Earth would instantly fly out of orbit. But Einstein's own rules said nothing can travel faster than light, not even the news of the sun's disappearance. It should take about 5 minutes for that news to reach us. This led Einstein to his masterpiece, general relativity. And the idea was breathtaking. Gravity is not a force. It's the curvature of spacetime. Think of spacetime as a stretched-out rubber sheet. Place a heavy bowling ball, the sun, in the middle. The sheet warps around it. Now, roll a marble, the Earth, nearby. The marble isn't being pulled by a mysterious force. It's just following the straightest possible path through the curved space. We see that path as an orbit. Mass tells space-time how to curve, and space-time tells matter how to move. It's a theory of pure geometry. And it's a proven fact. The GPS satellites orbiting Earth have to constantly correct their clocks because time literally runs faster for them in weaker gravity than it does for us on the surface. Without these relativistic corrections, your GPS would be off by miles every single day. So, what happens if we pull space and time apart? If there's no unified fabric, there's nothing to curve. The sun can't warp a spacetime that doesn't exist. The Earth would no longer follow an orbit because the path defining the orbit would be gone. Planets, stars, and galaxies would all fly apart. The cosmos would dissolve. Law 3. The conservation of energy and mass would fail. The law of conservation of energy is one of the most sacred rules in physics. Energy can't be created or destroyed, only changed. Einstein's famous equation, E equals mc squared, showed that mass is just a super-concentrated form of energy. This relationship is baked into the geometry of spacetime. In relativity, energy and momentum are two sides of the same coin, a four-dimensional vector called the four-momentum. When different people observe an object moving at different speeds, they'll measure different values for its energy. But what they all must agree on is the relationship between its energy, momentum, and its mass. The time dilation and length contraction we talked about are the precise adjustments reality makes to ensure these conservation laws hold true for everybody. Now, let's tear space and time apart again. Without that link, time dilation and length contraction are gone. An observer on a spaceship would look back at Earth and see our clocks and rulers as normal. But this would create a paradox. Without the proper relativistic corrections, different observers would calculate wildly different and incompatible values for the energy of the same object. The universe's accounting system would break down. E equals mc squared would no longer be a universal law. Depending on your point of view, energy could seem to appear from nothing or vanish completely. The idea that an object has a certain amount of energy stored in its mass would become meaningless. The universe's most fundamental bookkeeping would fall into total chaos. The deeper layers and the quantum wrinkle. If the story stopped with Einstein, it would be weird enough. But as physicists tried to unite his theory of gravity with the bizarre world of quantum mechanics, the relationship between space and time got even more mysterious. In the 1960s, physicists John Wheeler and Bryce DeWitt wrote down an equation that tried to describe the whole universe in a quantum way. But when they looked at their final result, something was missing. The letter T for time. In what could be the most fundamental equation of reality, time just vanishes. This is known as the problem of time, and it's one of the deepest puzzles in physics. It suggests that at the very bottom level of reality, there may be no such thing as time. Time might not be fundamental at all. Instead, it might be an asterisk emergent property, something that arises from a more basic, Timeless reality, much like wetness, emerges from H2O molecules. A single molecule isn't wet, but a group of them are. Maybe the fundamental atoms of spacetime don't experience time, but our macroscopic world, built from them, does. So where does our feeling of time's flow come from? One leading idea is that it comes from entropy, the universe's tendency to move from order to disorder. A glass can shatter into a million pieces, but a million pieces will never spontaneously assemble themselves back into a glass. This is the only law of physics that seems to have a built-in direction for time. What we call the flow of time might just be our perception of entropy on the rise. And the rabbit hole gets deeper. Think about quantum entanglement the spooky action at a distance that bugged Einstein so much. When two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. Some physicists now believe that spacetime itself might be built from entanglement. In this view, the geometry of space, the very idea of distance, is just a reflection of the network of quantum connections between particles. Entanglement doesn't happen in spacetime. Entanglement creates spacetime. If this is true, then space and time are inseparable because they are both woven from the same quantum threads. Trying to pull them apart would be like trying to separate the wetness of water from the water itself. This journey from Newton's clockwork universe to Einstein's warped fabric, and finally to a timeless quantum realm, shows us that the simplest questions are often the most profound. We saw how one stubborn fact, the constant speed of light, forced us to rethink everything. And in doing so, we found a universe held together by a single, beautiful, unified geometry. If you enjoyed this trip to the edge of reality, consider subscribing and hitting the bell so you don't miss our next exploration. And if you'd like to support what we do, liking the video really helps us know what kinds of questions you find most fascinating. So, why can't space and time be separated? Because they were never separate to begin with. That distinction only exists in our heads, a useful illusion for getting through the day. The universe doesn't have a where and a when. It has a unified spacetime, a four-dimensional stage whose very geometry dictates causality, creates gravity, and ensures the laws of physics work. Asking to pull them apart is, from the universe's point of view, a nonsensical question. It's like asking for a coin that only has a head side. They are two intrinsically linked aspects of one thing. And as we've seen, even this fabric may be a shadow of a deeper reality, a timeless, placeless quantum world where everything is connected. Our journey through time might just be our own consciousness sensing the universe's relentless march toward becoming a little bit messier. The illusion isn't that time exists. The illusion is that time exists by itself. The reality is a single, interconnected structure, far stranger and more beautiful than we ever imagined. And understanding that unity doesn't just change how we see physics, it changes how we see reality itself. What happens to your body if time stops cold? Imagine this. One moment you're walking down the street, maybe on your way to work, just lost in your own world. The next, everything stops. Not just the cars and the people around you, but time itself. You're caught mid-stride, your foot hovering inches from the ground, a perfect statue in a world that's become a photograph. A car hangs in the middle of an intersection, its driver frozen mid-blink. Raindrops are suspended in the air like tiny glass beads. A bird, wings outstretched, is simply locked in the sky. For a second, you might think you've just been handed a superpower. You're the master of the universe, a ghost in the machine, free to wander through this silent, still world. But that fantasy? It would dissolve almost instantly into a scientific nightmare. The reality is so much more terrifying. To finish that single step, just to let your foot touch the pavement, you'd have to break the most fundamental laws of physics. In this frozen reality, the first things to go are your sight and hearing, and the very air you need to breathe will become your unyielding, invisible prison. The steady march of time can feel like a restriction, always pushing us forward. But it's not a prison. The flow of time is what makes our existence possible. It's the framework that allows for motion, for change, for light, and for life itself. Stopping it, even for a second, would mean stopping everything that matters. So let's press the cosmic pause button. The universe is frozen, but we are not. What happens first? The sensory prison. A world without sight or sound. The very first thing that happens is nothing. A profound, absolute, and utterly deafening nothing. Your world goes black. Instantly. We almost never think about how our senses actually work. We just see. But your vision isn't passive, it's an incredibly active process. Sight works because tiny particles of light, called photons, travel from a source like the sun, bounce off everything around you, and then make a journey into your eyes. These photons hit your retina, which turns them into electrical signals that shoot down your optic nerve and into your brain. Your brain then acts like a supercomputer, processing these signals into the world you see. The key word in that entire process is travel. Photons have to move. But if time is frozen, every single photon in the universe is stopped dead in its tracks. They're locked in place, like a swarm of gnats frozen in amber. The light streaming from the sun is halted. The light reflecting off a person's face is fixed in the space between you. No new light can travel to your retinas. The last few photons that were just about to hit your eye will be the final thing you ever see. After that split second, it's over. You're plunged into a darkness more complete than any cave, deeper than the bottom of the ocean. The light is still all around you, but since it can't move, you can't see it. At the exact same moment, you're hit with an equally absolute silence. Sound, like light, isn't really a thing on its own. It's a vibration, a pressure wave moving through the air. When you make a sound, air molecules get pushed together and spread apart, creating a chain reaction that travels to your eardrums, making them vibrate. Your brain interprets those vibrations as sound. If time stops, all that molecular motion stops. The dance of air molecules grinds to a halt. The sound of a distant siren or a nearby conversation is frozen mid-vibration. It's no longer a wave, it's a static, invisible sculpture in the air. Nothing can travel to your eardrums to make them vibrate. You are instantly and completely deaf. So, in the first microsecond of your new reality, you're blind and deaf. You can't smell or taste anything either, for the same reason those senses rely on molecules traveling through the air or your saliva to reach receptors. If those molecules are frozen, your senses are useless. You are utterly alone, a single consciousness adrift in a sensory vacuum. Your body is still there, but the world it was built to interact with has just been switched off. But this is just the beginning of the horror. This is what happens when you do nothing. The real nightmare starts the moment you try to do something. The moment you try to move. Because the air around you, that invisible ocean of gas we swim through without a thought, has just become your tomb. The immovable wall, motion, and the prison of air. So there you are, floating in a silent, black void. Your first instinct, born of pure terror, is probably to panic. To scream, though no sound will come out. To wave your arms. To take a sharp, gasping breath. Go ahead and try. It won't work. You see, you're no longer surrounded by a gas. You are encased in a solid. We think of air as being mostly empty space. The molecules of nitrogen and oxygen are zipping around at hundreds of meters per second, but they're incredibly far apart. We move through them so easily we barely notice they're there. But with time stopped, that frantic motion ceases. Every single air molecule is frozen in place, locked into a rigid, invisible grid. The air has effectively become an immovable wall that perfectly surrounds every inch of your body. Now, think about that simple step you were about to take. To move your arm, to even twitch a finger, you'd have to physically shove trillions upon trillions of frozen nitrogen and oxygen molecules out of the way. But they can't move. They're locked in spacetime. Trying to push against them would be like punching a wall made of diamond that extends across the entire universe. You are held in place, perfectly and unyieldingly, by the very atmosphere you were just breathing. This isn't an analogy. It's a direct consequence of basic physics. Force equals the change in momentum divided by the change in time. In our scenario, what is the change in time? It's zero. And as anyone who's taken a math class knows, dividing by zero is a recipe for breaking everything. To make a single air molecule move to change its momentum at all, you would need to apply an asterisk infinite amount of force. Your muscles, no matter how strong, can't do that. You are completely and utterly paralyzed. This leads to the most immediate problem: breathing. To inhale, your diaphragm has to contract and your chest has to expand. But you can't expand your chest. The wall of frozen air prevents any movement. And even if you could, no new air could flow in. It's a solid. You can't exhale either. The air already inside your lungs is also frozen solid. You can't compress your chest to force it out. You're trapped, holding your breath for an eternity you can't even perceive. Let's take this a step further. What if you were in a perfect vacuum when time stopped? Would you be free then? The answer is still no. The problem isn't just outside you, it's inside you. For you to even decide to move your arm, your brain has to send an electrical signal. That signal is a flow of ions across the membranes of your nerve cells. This process, this flow, takes time. Milliseconds, yes, but still time. If time is stopped, the flow is frozen. The signal from your brain can never reach your muscles. Your own will is trapped inside your mind. And even if the signal could magically arrive, your muscles themselves couldn't act on it. Muscle contraction is a beautiful piece of biological machinery where proteins slide past one another, a process powered by chemical energy. Every single step of this process is a physical movement that happens over time. Without time, the muscle fibers are locked. They can't function. You're a statue, inside and out. Your body is a prison, and the bars are made of frozen atoms. You're blind, deaf, and paralyzed, trapped in a single, unchanging moment. The world hasn't just stopped for you, you have stopped with it. So we're trapped. A conscious mind in a body that can't move, in a universe that cannot change. It's a terrifying thought, but it shows you just how deeply the idea of change is woven into reality itself. Everything we've talked about so far, light, sound, motion, is a form of change. And change needs time. But what about things that seem static? What about heat? Or the fabric of space itself? If you think it's been a nightmare so far, you'll want to stick around. The real breakdown is about to begin. If thought experiments like this are your thing, consider subscribing to the channel. We go deep on questions like this every week, and you won't want to miss where this one goes next. The cosmic breakdown, heat, energy, and relativity. We've built our own personal hell, a silent, dark, motionless prison. But our individual problem is just a tiny symptom of a universe-wide catastrophe. The laws of physics haven't just been paused, they've been shattered. Let's start with something as basic as temperature. What is heat? When you feel something hot, you're feeling the transfer of energy. The atoms in a hot object are vibrating incredibly fast. When you touch it, that vibration is transferred to the atoms in your hand, and your nerves read that as hot. Temperature is just a measurement of how fast the atoms and molecules in something are moving. So what happens to temperature when time stops? All motion ceases. The frantic vibration of atoms in a star, the slow jiggling of molecules in your chair, it all just stops. If there's no motion, then the kinetic energy of every particle in the universe drops to zero. This means the entire universe instantly plunges to absolute zero. Absolute zero, or 0 Kelvin, is the coldest possible temperature, the point where all atomic motion is supposed to stop. It's so cold we can't even reach it in our labs. But in our time-stopped universe, we're there. Every star, every planet, every living thing is instantly at absolute zero. The very idea of heat becomes meaningless. But even this pales in comparison to what happens to reality itself. For this, we have to turn to Albert Einstein. He showed us that space and time aren't separate things. They're woven together into a single, four-dimensional fabric called spacetime. Gravity isn't a force pulling things together. It's just what happens when mass and energy bend and curve that fabric. Think of it this way. Even if you're sitting perfectly still, you are still moving through time. But what happens if we stop time? The time dimension of our spacetime fabric just vanishes. It's gone. The four-dimensional reality we live in collapses into a static, three-dimensional space. Every object's path through history and into the future collapses into a single point. You can't move from point A to point B because there's no time to travel during your trip through space. Einstein's work also tells us that the faster you move through space, the slower you experience time. For a particle of light, which travels at the ultimate speed limit, no time passes at all. Its entire journey across billions of light years is, from its perspective, instantaneous. So what happens if time stops for the entire universe? The whole framework shatters. The speed of light is a distance traveled over time. If time is zero, the speed of light becomes meaningless. Nothing can move. Because you can't stop time without also destroying space, the very concept of distance itself begins to fall apart. It's a paradox our physics can't answer, because all of our physics is built on one core assumption. Time moves forward. Without time, gravity stops working. The Earth is no longer bound to the Sun. The Sun is no longer held together by its own gravity. Of course, that hardly matters, because the nuclear fusion in the Sun's core would have also stopped. The fundamental forces of the universe, gravity, electromagnetism, the nuclear forces, all describe things that happen in time. Without it, the entire rulebook of the cosmos has been deleted. The philosophical void, the death of consciousness and meaning. So we've dismantled the universe, piece by piece. Sight, sound, motion, heat, and space-time have all dissolved. We're left as a paralyzed statue in a universe frozen at absolute zero, where the laws of physics no longer apply. But what about your mind? Could your consciousness, your inner world of thoughts and feelings, keep going in this timeless void? Based on everything we know about the brain, the answer is a final, definitive no. What is a thought? While consciousness itself is a huge mystery, we know the processes behind it are physical. A thought isn't a static thing. It's a dynamic pattern of millions of neurons firing in a complex symphony. And as we've established, that process requires time. The movement of ions, the release of chemicals across a synapse, the binding to the next neuron, it's a chain reaction. If time stops, that chain reaction is frozen mid-step. A thought that was in the process of forming is locked, incomplete, forever. You can't have a before and after in your own stream of consciousness. The very act of thinking is based on the passage of time. A single, frozen snapshot of your brain's network isn't consciousness, any more than a single frame from a movie is the movie itself. Without the progression from one frame to the next, there's no story, no experience. Even if you argue that consciousness is more than just physical, the problem remains. How can you be aware of a timeless state? Being aware means there's a you and a thing you're aware of, and that separation implies a moment of reflection, which itself takes time. You can't experience now unless it's different from before and after. If there's only one single, eternal Now, the concept of experience itself loses all meaning. This leads us to the ultimate breakdown, the collapse of cause and effect. Causality is the simple rule that an effect has a cause, and the cause comes first. In a timeless universe, there is no before and no after. Cause and effect are meaningless. Nothing can happen, because happen is a verb, and verbs need time. And this brings us to the final, haunting question. If you could somehow remain a thinking ghost in this frozen cosmos, what meaning would you find? Our lives are defined by their story, by the journey. We are the sum of our memories and we live in anticipation of our future. Happiness, love, ambition, all of these are processes, not states. If life is a song, does a single, infinitely held note contain any music? Perhaps the most unsettling conclusion is not the physical horror, but the philosophical horror of ultimate meaninglessness. Meaning isn't something that exists in a moment, but something created across moments. It's the journey, the change, the becoming, that gives life its substance. Take away time, and you take away the story. So, what happens to your body if time stops cold? You're plunged into a silent, black void. You become an immovable statue, encased in solid air, unable to move or breathe. The entire universe instantly plummets to absolute zero. The fabric of spacetime shatters, erasing the laws of physics. And finally, your own consciousness, the stream of thoughts that is you, would simply cease. The fantasy of mastering the universe dissolves into the ultimate nightmare of non-existence. You wouldn't be a victim. You wouldn't be anything at all. No one would ever notice that time had stopped, because the very ability to notice would be one of its casualties. If time were to restart, it would be as if nothing ever happened. This thought experiment, as wild as it is a powerful reminder. Time isn't just a clock on the wall. It's not an enemy to be beaten. The steady, forward march of time is the pillar that holds up all of reality. It's the invisible current that allows for motion, change, light, life, and meaning. Every step you take, every breath you draw, every thought you have is a testament to its power. The flow of time is what makes everything else possible. But what if we could do more than just stop it? What if we could control it, bend it, or even travel through it? What new paradoxes would arise if we could actually revisit the past? Well, that's a thought experiment for another day. If you enjoy wrestling with these kinds of mind-bending questions, make sure to subscribe and hit that bell icon so you don't miss our next journey into the impossible. And check out our other video, What If You Fell Into a Black Hole?, for another look at what happens when the laws of time and space get pushed to their absolute limits. The cosmic glitch that unlinks before and after. Cause, then effect. It's the simplest rule in the universe. You flip a switch, a light turns on. You drop a glass, it shatters. First this, then that. It's a neat, tidy little chain of logic that holds our reality together. But that entire chain, everything we know depends on one tiny, overlooked thing: distance. The space between the cause and the effect. So, what if it wasn't there? What if you could just erase it? Compress the entire cosmos, every star, every planet, you, me, into a single point. Without distance, the idea of one thing happening before another completely shatters. The link is broken. Today, we're going to explore this terrifying cosmic glitch, a theoretical flaw in the fabric of reality itself. And it's going to force us to ask a deeply unsettling question. Is time, as we know it, just an illusion created by space? The unbreakable law. Alright, so before we go about breaking the universe, we should probably understand the rules. Our story starts with something so basic we barely even think about it: causality. The unbreakable law that an effect can't happen before its cause. This isn't just a good idea, it's the bedrock of a sane universe. It's what lets us build things, plan for the future, and make sense of the past. But for this law to work, you need two key ingredients: time and space. Think about it. For a cause to create an effect, some kind of signal has to travel from point A to point B. That journey needs a stage to happen on that space. And it needs a duration for the trip to unfold, that's time. In the old school physics of Isaac Newton, these two things were completely separate and absolute. Newton saw space as this rigid, 3D grid, an infinite box where everything happened. And time? He imagined a single, universal clock, ticking away at the exact same rate for everyone, everywhere. Whether you were sitting on Earth or zipping past Jupiter, that clock ticked in perfect sync. It was simple, it was intuitive, and for a couple of hundred years, it was the law. But as it turns out, nature is a lot weirder than that. At the turn of the 20th century, this whole elegant picture started to fall apart. And the crisis started with light. Scientists figured that light, like any other wave, needed something to travel through. They called it the luminiferous ether, a hypothetical substance filling all of space. The problem? Every single experiment to find this ether, like the famous Michelson-Morley experiment, came up empty. It was as if the ether just wasn't there, and even weirder, the speed of light was always, impossibly, the same. It didn't matter if you were flying towards a light beam or away from it. You'd always measure its speed to be exactly the same. This was a huge paradox. It broke everything we thought we knew about motion. Physics had hit a wall. And it took a rebellious patent clerk in Bern, Switzerland, to show everyone the way out. Albert Einstein realized the problem wasn't the experiments, it was our assumptions. He proposed something revolutionary. The speed of light isn't just constant, it's the ultimate speed limit of the universe. And for that to be true, our neat and tidy ideas of absolute space and absolute time had to go. This is where things get really interesting. Einstein's theory of special relativity showed that space and time aren't separate at all. They're woven together into a single, four-dimensional fabric, spacetime. And this fabric isn't just a passive backdrop. Its geometry dictates the laws of physics. So why are they fused? It all comes back to that constant speed of light. If two people are moving at different speeds, they both have to measure a beam of light as moving at the same speed. The only way the math works out is if their personal experience of space and time is different. One person's second isn't the same as another's. One person's meter is longer or shorter than another's. Space and time have to literally stretch and shrink for each person, just to keep the speed of light constant for everyone. This led Einstein to a profound discovery, the spacetime interval. It's the cosmic glue that holds causality together. Think of it this way. If you and a friend look at a tilted table from different angles, you might disagree on its length and its width. But you'll both agree on the length of its diagonal if you use the Pythagorean theorem. The diagonal's length is invariant. The spacetime interval is the 4D version of that diagonal. It's a calculation that combines the distance between two events in space with the time that passes between them. And the incredible part is, no matter how fast you're moving, no matter how much your personal ruler and clock are warped, the spacetime interval between those two events is the asterisk exact same for every observer in the universe. It's the ultimate, objective truth. This interval determines whether one event could have caused another. If there's more time than space in the interval, we call it time-like. A signal could have made the journey. One event can cause the other. If the interval is exactly zero, we call it light-like. Only light itself could connect the two events. And if there's more space than time, we call it space-like. The two events are so far apart that not even light could have traveled between them. They are completely, causally disconnected. One could not have caused the other. End of story. This structure is the foundation of our reality. It keeps things logical. It makes sure effects follow their causes. But what happens if we decide to smash this foundation? What happens if we trigger the glitch? The cosmic glitch. We've got the law. Spacetime is a unified fabric that keeps cause and effect in line. But progress comes from asking, what if? So let's run the most extreme thought experiment imaginable. What if we could peel space away from time, undoing Einstein's work and creating a universe where only time exists? Let's call this the cosmic glitch. Imagine a knob that controls the spatial separation of the universe. We turn it down. The distance between you and the wall shrinks. We turn it down more. The Earth and Sun are now neighbors. Now, let's crank it all the way to zero. Poof! The spatial distance between any 2 points is now zero. Every star, every atom, you occupies the exact same, single point. There is no here and there. Only a single spot containing the entire cosmos. The implications are instantly terrifying. How does the sun warm the Earth if they're occupying the same space? How do you see a star? In our universe, its light takes billions of years to cross that distance. In the glitched universe, there's no distance to cross. The star and your eyeball are in the same place. Does the light arrive instantly? Does arrival even mean anything? This is the core of the paradox. We've built physics on a 4-dimensional stage. By ripping out the 3 spatial dimensions, we've torn down the stage itself. All the actors, the particles and forces are just piled in a heap with no room to move or interact. And right here, the laws of physics just break. Motion becomes meaningless. How can you move if there's nowhere to move to? Velocity is distance over time. If the distance is always zero, velocity is always zero. The entire universe is frozen in perfect, absolute stillness. But what about time? In this single point containing everything, could time still tick forward? Could one moment still follow another? We have a universe with no where, but can it still have a when? Could we get a sequence A, then B, then C all happening at this one spot? By breaking space-time, have we destroyed time itself, or have we accidentally revealed its true nature? Unlinking time. So, we're in the glitch. A universe crushed into a single dot. To figure out what happens to time, we have to see what parts of it, if any, can survive. What happens to sequence, to flow, and to the arrow of time? First, sequence. Can one event still happen after another? The answer, surprisingly, is a very limited yes. To see why, we need to talk about proper time. In relativity, there's no master clock. Everyone's clock ticks differently based on how they're moving. But proper time is the time measured by a clock you're holding in your hand, one that's moving along with you. It's your own personal time. Now, here's a wild principle of spacetime. Objects traveling between 2 points without being pushed or pulled following a straight line through spacetime called a geodesic will experience the most possible proper time. This is the secret behind the twin paradox. The twin who stays on Earth is on a straighter path through space-time, moving mostly through the time dimension. The traveling twin takes a curved path, mixing space and time travel. When they reunite, the stay-at-home twin has experienced more proper time. They're older. So, let's go back to our glitch. Everything is stuck at a single point. There's no motion through space. This means every object is forced to follow the straightest possible path through spacetime, a path only through the time dimension. In a way, everyone is the stay-at-home twin. This means a sequence is still possible. Event A can happen, then event B, then event C, all at this one point. We can still have a history and a future. We've preserved the basic order of before and after. Think of it like a reel of film. The frames are in a clear sequence. Our glitched universe still has that reel. But we've lost the projector screen. We have a sequence, but nowhere for the events to actually happen. And this is where it gets bad. Because this brings us to the real question. Can time flow? We feel time as a continuous river. But what is that flow, physically? How does a clock measure it? This is where our glitch turns into a catastrophe. Let's use Einstein's favorite imaginary clock, a light clock. It's just two mirrors with a photon bouncing between them. Each bounce is a tick. The time per tick is set by the distance between the mirrors and the speed of light. Easy. Now, activate the glitch. We shrink the distance between the mirrors. The ticks get faster and faster. Less distance to travel. Now, shrink the distance to 0. What happens? The mirrors are touching. The photon has nowhere to go. It can't travel. It can't bounce. The clock doesn't tick. It's frozen. The very mechanism of the clock is broken because it needed space to work. And this isn't just a problem for our light clock. It's a problem for every clock. An atomic clock works by measuring the oscillations of electrons in an atom. But an atom has a physical size. Shrink that to 0, and the physics breaks down. The clock stops. Your biological clock is driven by chemical reactions in the spatial volume of your cells. Without space, there's no biology. The clock of life itself grinds to a halt. What our glitch reveals is that the flow of time isn't some magical, independent thing. It's tied to physical processes happening in space. Time doesn't just pass, it's measured out by stuff moving across distances. By removing space, we removed the ability for anything to happen. We have a sequence of moments, but the duration between them is 0. We have the film frames, but the film can't advance. And it gets worse. In our universe, every event creates a light cone, the region of space-time it can influence in the future. It gives us choices, a vast cone of possible paths. But in our spaceless glitch, we remove the 3 spatial dimensions, and that cone collapses. It shrinks into a single, vertical line. Your future is no longer a web of possibilities. It's a single, predetermined track. Causality is flattened. There's no room for choice or chance. Everything is locked onto a one-dimensional rail. Finally, what about the big laws? The second law of thermodynamics, time's arrow, says that disorder, or entropy, always increases. But for things to get disordered, they need space to spread out and get messy in. In a zero-space universe, there's no room for mess. The law becomes meaningless. And gravity? General relativity says mass curves spacetime. If there's no space, there's no fabric to curve. The theory of gravity just evaporates. So by removing space, we found that time survives only as a skeleton, a sequence of events. The flow, the duration, the ticking of clocks all gone. Causality is a flat line. The great engines of change are switched off. The illusion of now. Our little trip into a spaceless universe has revealed something deeply weird. We found that time as we know it shatters. Its flow, its arrow, its mechanics, they all depend on space. And this forces us to confront a radical possibility about our own reality. If our experience of time is this fragile, maybe that experience isn't fundamental. Maybe the flowing, present moment is just a profound illusion. This brings us to a mind-bending idea from physics and philosophy, the block universe theory. This theory says our feeling of time's flow is just plain wrong. It suggests that just like all of space exists at once, all of time past, present, and future also exists at once. They're all equally real, laid out in a 4-dimensional block of spacetime. Think of the universe as a book. The whole book already exists. The first page, the middle, the end, they're all there. As you read, your consciousness creates the sense of a story flowing by page. You have a present page, a past you remember, and a future you haven't read. But your act of reading doesn't change the fact that the entire story exists as a complete, static object. The block universe theory says reality is that book. Our consciousness is just the reader, moving along the time dimension and creating the powerful illusion of a flowing now. We feel like the past is gone and the future isn't written, but in this view, the past is still there, and the future is too. Our cosmic glitch experiment is like we broke the projector. We were left with just the raw film strip, the static, ordered sequence of events. By taking away space, we stripped away the illusion of a dynamic, flowing present and were left with the stark reality of the block. This changes everything. It suggests our feeling of now isn't a property of the universe, but a property of our minds. It's a side effect of our biology, which evolved to experience reality sequentially because we live and move in a world of space. We are creatures of space, and so we experience time as a product of it. If this is true, time doesn't flow. It simply is. The dinosaurs aren't gone. They're just in a different part of the spacetime block. Your future isn't a world of open possibilities. It's just a part of the timeline your consciousness hasn't reached yet. The universe is a finished sculpture, and we're just seeing it from one angle at a time. Living in the glitch. So what did we find? We started with cause and effect, saw how Einstein wove them into spacetime, and then we broke it. We surgically removed space from reality. And in that void, we made a startling discovery. Time, on its own, is a ghost. The sequence of before and after hangs on, but the flow of time, the ticking of a clock, the feeling of duration stops dead. Every physical process that marks time needs space to work. The feeling of a rushing present, the memories of a fixed past, the hopes for an open future, it seems to all be a product of our existence in space. The duration we feel is a side effect of the distance between things. This brings us back to that ultimate question. If time's flow is an illusion generated by space, what does that mean for us? Are we just passive observers, our consciousness reading the pages of a book that's already been written from beginning to end? Is your future already out there, set in stone, waiting for you in the block universe? What do you think? Does this cosmic glitch reveal a deep truth about reality? Or is it just a sign that our theories have limits? Is time real, or is it the most convincing illusion of them all? Let us know what you think in the comments. We love diving into these conversations and hearing your perspectives. And if you want to keep questioning reality with us, make sure to subscribe and ring that bell. The universe is full of glitches, and we've only just scratched the surface. The secret fusion that makes speed possible. You think you know what speed is? Distance divided by time. Simple, right? A car travels 100 kilometers in an hour. A sprinter covers 100 meters in under 10 seconds. It's one of the first formulas we ever learn, a bedrock idea that seems to govern everything from a casual stroll to a rocket launch. But that simple formula, that idea that seems so obvious, hides a mind-bending truth. The concept of speed, of any motion at all, is only possible because of a secret fusion happening at the very fabric of reality. A fusion of space and time. In the next few minutes, you'll see that you aren't just moving through space. You're on a constant, unwavering journey through something called space-time. And understanding this will change how you see everything that moves. The world of common sense. For most of human history, our idea of motion was built on what you might call common sense. It's a world that just feels right, a world put into words by two of the greatest minds in science, Galileo Galilei and Isaac Newton. Let's start with Galileo. In the early 1600s, he gave us a beautiful idea. The principle of relativity. He asked you to imagine being in the windowless cabin of a ship, moving at a constant speed on a perfectly calm sea. Could you even tell you were moving? If you dropped a ball, it would fall straight to your feet, just like it would on land. A fly buzzing around wouldn't get slammed into the back wall. Galileo realized that inside that cabin, all the laws of physics work exactly as they would if the ship were docked. The only way to know you're moving is to look out and compare your position to something else, like the shore. This is Galilean relativity. All steady motion is relative. There's no such thing as being absolutely still. This is baked into our experience. When you're on a smooth train and the one on the next track starts to move, there's that weird moment where you can't tell if you're moving forward or the other train is moving backward. Your motion only makes sense relative to something else. Then, about 50 years later, Isaac Newton took this idea and built a cathedral of physics on top of it. His laws of motion and universal gravitation described the world with stunning accuracy. They could predict the arc of a cannonball, the orbit of the moon, the fall of an apple. And his entire system rested on two giant, unshakable pillars. The first was absolute space. Newton saw space as a huge, unchanging, 3D stage. A fixed grid where all the events of the universe played out. Your location could be nailed down with 3 coordinates on this grand cosmic map. Space was the container. Everything else just happened inside it. The second pillar was absolute time. For Newton, time was a universal river, flowing at the exact same rate for everyone, everywhere. A second on Earth was a second on Jupiter and a second in the most distant galaxy. My now was your now, no matter where we were or how fast we were moving. This cosmic clock just ticked on, ignoring everything. In this Newtonian world, speed is wonderfully simple. It's exactly what you learned in school. If space is the absolute stage and time is the absolute clock, speed is just how much stage you cover in a certain number of ticks. And speeds add up like you'd expect. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 20, someone on the ground sees the ball moving at a simple 120 kilometers per hour. This is the world of our intuition. It's logical, it's orderly, and for over 200 years, it seemed perfect. Newton's physics was so good it felt like he'd found the final rules of the universe. But in the quiet halls of 19th-century science, a ghost was creeping out of the math. A phantom that would eventually bring the whole magnificent structure crashing down. The universal speed limit. The first crack in Newton's perfect world didn't come from studying cannonballs or planets. It came from light, electricity, and magnetism. In the 1860s, a Scottish physicist named James Clerk Maxwell pulled off one of the greatest unifications in science history. He wove these 3, seemingly separate things together into a single, elegant set of 4 equations. But buried in his equations was a prediction so bizarre, so contrary to common sense, that physicists spent decades trying to figure it out. The math said that light was an electromagnetic wave and that this wave traveled at a very specific, unchanging speed. This speed, called c, was about 300,000 kilometers per second. Now, that might not seem so weird at first. But the immediate question was constant relative to what? Remember Galileo's ship? A ball's speed is relative to the ship or the shore. Sound travels relative to the air. Every wave we knew about needed a medium to travel through. So, physicists figured light must have one, too. They called this hypothetical stuff the luminiferous ether. It was supposed to be a massless, invisible ocean that filled all of space, through which light waves rippled. And the Earth, orbiting the Sun, must be plowing through this ether. This gave them a clean answer. The speed, c, must be the speed of light relative to the stationary ether. That meant our own motion through the ether should change the speed of light we measure. If you're moving into the ether wind, light should seem to come at you a bit faster. Move with it, and it should seem a bit slower. Simple. This was a perfectly testable idea. In 1887, 2 American physicists, Albert Michelson and Edward Morley, set out to test it. They built an incredibly clever device called an interferometer. It split a beam of light, sent the 2 new beams on perpendicular journeys of the same length, and then brought them back together. If one beam was slowed down by the ether wind more than the other, their waves would be out of sync when they recombined, creating a telltale pattern. They set up their experiment with extreme care. The whole thing was built on a massive stone slab floating in a pool of mercury to damp out any vibrations. They rotated it, expecting to see the pattern shift as the device changed its angle to the ether wind. They ran the experiment. They checked their results. They ran it again at different times of day, different times of year. And they found nothing. Absolutely nothing. No matter how they turned it, the speed of light was always the same. It was a failed experiment, but it might be the most important failure in the history of science. It flew in the face of everything they knew. Think about it. If you're on a spaceship going half the speed of light and you turn on a flashlight, common sense says someone watching you fly by should see that light beam moving at 1.5 times the speed of light. But Michelson and Morley's result was screaming that this is wrong. Both you on the ship and the person on the ground would measure that light moving at exactly c. This is where our intuition just shatters. How can something move at the same speed relative to you whether you're standing still or chasing it? It's like throwing a baseball and having it move away from you at 50 miles per hour, while someone you're running towards also sees it approaching them at only 50 miles per hour. It makes no sense. Physicists scrambled to save the ether. Maybe the Earth drags the ether along with it? Nope, other experiments ruled that out. Maybe moving objects literally shrink in the direction of motion? This idea, from Fitzgerald and Lorentz, was a mathematical patch, but it felt like a desperate fix. The classical world of Newton was broken. The elegant simplicity of "speed equals distance, time" was built on a foundation that was now cracking under the weight of one stubborn fact: the unwavering, absolute speed of light. Physics was in crisis. It would take a mind unbound by tradition, a young patent clerk in Bern, to see that the problem wasn't with light. The problem was with space and time themselves. Einstein's revolution. Enter Albert Einstein. In 1905, he was haunted by this paradox. He'd been thinking about it since he was a teenager, when he tried to imagine riding alongside a beam of light. In Newton's world, if you matched its speed, the light wave should look frozen next to you. But Maxwell's equation said that could never happen. Light is always on the move. Everyone else was trying to force light to obey the old rules. Einstein's genius was to flip the problem on its head. He asked a bolder question. What if the experiment is right? What if the speed of light is the one thing that's absolute? If we take that as an unbreakable law, then what else has to break? His answer was radical. The things Newton considered absolute and unshakable, space and time, were, in fact, flexible, malleable, relative. This is the secret fusion. Einstein realized that space and time are not two different things. They aren't a static stage and a universal clock. They are woven together into a single, four-dimensional fabric, spacetime. This was the core of his special theory of relativity, built on two powerful ideas. 1. The laws of physics are the same for everyone in uniform motion. No one has a special, at rest, point of view. 2. The speed of light in a vacuum, c, is the same for all observers, no matter what. Everything else, all the weird and wonderful consequences of relativity, flows from this. If the speed of light is the one thing that cannot change, then space and time themselves must conspire to make it so. They have to stretch and shrink to ensure that every single person, no matter their speed, measures a light beam at exactly 299,792, 458 meters per second. Go back to our formula. Speed equals distance, time. If speed of light is the constant, then distance, space, and time have to be the variables. They are no longer the reliable rulers and clocks of Newton's world. Hermann Minkowski, one of Einstein's old professors, put it best. Henceforth, space by itself, and time by itself, are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. This is the secret fusion. It's not just a cool idea. It's the fundamental geometry of our universe. An event isn't just a point in space anymore. It's a point in four-dimensional spacetime, a specific location in space at a specific moment in time. Your whole life is a path through spacetime, a world line. And in this new reality, the thing that all observers agree on isn't distance or time, but the asterisk spacetime interval asterisk between two events. It's a new kind of 4D distance. It's calculated with an equation that looks a bit like the Pythagorean theorem, but with a crucial twist. A minus sign. Delta S squared equals C delta T squared delta X squared . That minus sign is everything. It's the secret sauce. It mathematically separates time from space, even as it fuses them. In geometry, A squared plus B squared equals C squared . But in reality, it's more like A squared minus B squared equals C squared . This peculiar math is what creates all the bizarre effects of relativity. It's the deep reason why you can move back and forth in space, but only forward in time. The old world of absolute space and time was just an illusion, a very convincing one that works fine at the slow speeds of our everyday lives. But the moment you get close to the speed of light, the illusion shatters, and the true, fused nature of spacetime reveals itself. The new reality of motion. So, what does this fused spacetime actually mean for speed? It means we have to completely rethink what it means to move. And the best way to do that is with an analogy. Imagine that all your motion is a journey through the four dimensions of spacetime. And here's the key idea. Everything in the universe is traveling through spacetime at one single, constant speed, the speed of light. Stick with me here. This is the new reality. You, me, this planet, a speeding bullet. We are all on a journey through spacetime, and the speed of that journey is always c. Now, think of this spacetime speed as an arrow with a fixed length. That length is c. This arrow can point in different directions within spacetime. It has one part pointing through time and three parts pointing through space. When you're sitting perfectly still, at rest, in space, your arrow is pointing straight into the future. All of your motion is being used to travel through the dimension of time. You aren't moving through space, so you are traveling through time at the maximum possible rate. Now, what happens when you stand up and walk? You start moving through space. To do that, you have to rotate your spacetime arrow. You divert a tiny bit of your motion from the time direction and point it into the space direction. And because the total length of your arrow must stay c, the more you move through space, the less you can move through time. The mind-blowing consequence is this. The faster you move through space, the slower you move through time. Asterisk. What we call speed is just a measure of how much of our constant spacetime motion we're using for space travel. It's a trade-off. You can spend your motion budget on traveling through time or on traveling through space, but the total budget is fixed. This one idea elegantly explains all the weird effects of special relativity. First, time dilation. If a spaceship zips past you, its spacetime arrow is tilted more towards space than yours. That means its arrow in the time direction must be shorter. From your perspective, its clocks are literally ticking slower. Time itself is passing more slowly for the spaceship. This has been proven. Tiny particles called muons, when sped up to near the speed of light, last far longer than they should, exactly as the theory predicts. Second, length contraction. It's the other side of the coin. For the speed of light to stay constant for everyone, space has to shrink, too. That same spaceship will appear, to you, to be squashed in its direction of motion. The people inside, however, don't notice a thing. To them, it's the rest of the universe that looks squashed. Third, the asterisk relativity of simultaneity. This might be the strangest part. In Newton's world, now was universal. In space-time, two events that happen at the same time for you could happen at different times for someone moving past you. There is no absolute, universal, now. Your now is a slice through space-time, and someone else's slice is tilted relative to yours. We don't all share the same present moment. So, the very idea of speed is impossible without this fusion. Speed is what forces space and time to become relative. A high speed is what reorients your path through space-time, stretching your time and shrinking your space in the eyes of someone else. Without this flexible space-time, the constant speed of light would be impossible. The cosmic speedometer. This new understanding also gives us a profound insight into the ultimate speed limit. Why can't anything with mass reach the speed of light? As you go faster through space, you're rotating your space-time arrow more and more towards the space direction. To reach the speed of light through space, you'd have to point your arrow entirely in that direction. This would mean your motion through time would drop to zero. From an outside perspective, time would stop for you. But there's more. As you push an object closer to its resistance to going any faster, its inertia increases, approaching infinity. Getting it that last little bit to the speed of light would take an infinite amount of energy. It's impossible. Only massless particles, like photons of light, travel at the speed of light. For them, it's the only speed they can have. They travel exclusively through space, and from their point of view, no time passes at all. A photon from a star billions of light years away experiences its entire journey from star to your eyeball in a single, timeless instant. And this isn't just abstract theory. You use this fusion of space and time every single day, thanks to the Global Positioning System, or GPS. Your phone figures out where it is by timing signals from satellites orbiting the Earth. But those satellites are in a tricky situation. First, they're moving fast, about 14,000 kilometers per hour. Because of their speed, special relativity says their clocks should tick slower than ours by about 7 microseconds every day. But that's not all. They're also 20,000 kilometers up, where Earth's gravity is weaker. This brings in Einstein's general relativity, which says gravity is a curve in spacetime. Time actually runs faster in weaker gravity. For the GPS satellites, this effect makes their clocks run faster than ours by about 45 microseconds a day. Combine the two effects, and the satellite clocks get ahead of ground clocks by a net 38 microseconds every single day. That's 38 millionths of a second. It sounds tiny, right? But GPS relies on timing accurate to the nanosecond. If engineers had ignored relativity and just used Newton's physics, your GPS would be worse than useless. The errors would add up so fast that after just one day, it would think your house was 10 kilometers away. The fact that you can navigate to a coffee shop is daily, concrete proof that spacetime is real. If this new way of seeing the universe blows your mind, let us know in the comments what concept you'd like us to tackle next. And if you want to keep exploring the fundamental nature of reality, make sure to subscribe. The grand perspective. We started with speed equals distance, time . It felt solid, intuitive, true. It was the common sense view of a clockwork universe. But then a single, stubborn fact, the absolute speed of light, blew it all up. To save that one fact, Einstein had to demolish the old foundation and reveal the deeper truth hidden underneath, the secret fusion of spacetime. In this new universe, speed isn't just about covering distance. It's about a fundamental trade-off, a rotation of your path through a four-dimensional reality. The faster you race through space, the slower your journey through time. The speedometer in your car is more than a gauge of motion. It's a window into the interwoven fabric of the cosmos. It's a measure of how you're spending your constant, universal velocity through spacetime. So, the next time you see something move, a bird, a plane, or just your reflection as you walk past a window, remember the secret. You're not just watching an object move through space. You are witnessing an act of cosmic barter. You are seeing a path being charted through the unified landscape of spacetime, a landscape where the very idea of speed is born from the deepest fusion in the universe. The terrifying world without cause and effect. Imagine a glass shattering on the floor. Then, a moment later, a rock hanging in midair starts to move toward the spot where the glass used to be. The effect arrives before the cause. The consequence comes before the action. Now, this isn't a prediction from some doomsday prophecy. It's a thought experiment, a what if scenario that lurks in the deepest corners of modern physics. It's what happens when you start to pick at the fundamental link between space and time, the very foundation of our reality. We live our lives on an invisible thread, a principle so basic we barely notice it's there. The law of cause and effect. It tells us that every action has a reaction, that the past shapes the present, and the present builds the future. It's why we can remember, plan, learn, and even love. It's the source of all order in the universe. But what if that thread could snap? What if the universe wasn't a story written from beginning to end, but a chaotic jumble of sentences, where the last page could influence the first? Physics itself has started to hint at this strange possibility. It suggests that our perception of a neat, linear flow of time might be just a convenient illusion. And if that illusion shatters, the world we know might just shatter with it. Here's a truly unsettling idea that has come out of physics. Space and time aren't the separate, independent things we experience them to be. They are woven together into a single fabric, a continuum we call spacetime. But this is where it gets critical. If you pull them apart in a thought experiment, if you sever the connection between the where and the when, the principle of causality itself, the absolute law that a cause must come before its effect, seems to fall apart. This isn't just an abstract equation on a blackboard. It has profound, and frankly, pretty terrifying implications for how we think about reality, the stability of our memories, the freedom of our choices, and the very meaning of our existence. We are about to venture into a world governed by this broken logic. A world where the future might be connected to the past in ways we can't imagine. A world where the comforting arrow of time isn't just bent, but tangled. Prepare yourself, because we're about to stare into the abyss of a universe without cause and effect. The arrow of time, our prison and our salvation. Before we dive into that chaos, let's first appreciate the world we actually live in, a world governed by what feels like an invisible but ruthlessly efficient tyrant. The arrow of time. Think about it. You can remember the past, but you can't remember the future. You can be held responsible for something you did, but not for something you will do. A domino falls, then it hits its neighbor. This one-way street is the most fundamental experience we have. It's so deeply ingrained in our minds that questioning it feels like questioning our own sanity. This forward march of time isn't just a feeling, it has a name in physics. The second law of thermodynamics. At its heart, this law says that over time, the total amount of disorder, or entropy, in a closed system like our universe, will always increase. An egg can become scrambled, but you'll never see a scrambled egg spontaneously unscramble itself. A building can fall into rubble, but rubble won't assemble itself into a building. This constant increase in entropy is what gives time its direction. It's the universe's way of making sure events unfold in a logical, predictable sequence. It's the metronome that keeps the symphony of reality in rhythm. This linear causality is more than just a physical rule. It's the architect of our entire civilization. Every plan you make, from a meeting tomorrow to saving for retirement, is an act of faith in a predictable future born from present actions. Our entire legal system is built on the idea that an act, the cause, leads to a consequence, the effect. Our sense of self is a story we tell, built from a coherent sequence of memories. You are who you are today because of what happened yesterday and the day before. Your memories are the footprints left behind by the forward march of causality. Without this arrow of time, learning would be impossible. We learn from our mistakes because we feel the negative effect after we make the mistake. If you could feel the pain of touching a hot stove before you reached out your hand, what lesson would you learn? The connection would be broken. There'd be no feedback, no consequence, no way to grow or adapt. Every moment would be an island, totally disconnected from what came before and what will come after. In our classical, predictable world, causality is our anchor. It gives us the stability and order needed for life and consciousness. It's a prison, in a sense we're trapped in this relentless, one-way flow, but it's also our salvation. It's the framework that gives our actions meaning. But, as physicists began to probe the very, very small, they found a crack in this foundation. A fracture that threatens to bring the whole orderly world tumbling down, at least in our minds. And it all starts with a simple experiment involving two slits. The first crack, a slit in reality. Our journey into chaos begins not in the vastness of space, but in the ghostly world of quantum mechanics. For centuries, our classical understanding of falling apples and orbiting planets was enough. But when we built tools sensitive enough to see individual particles like electrons, reality started acting in ways that defied all common sense. The most famous, and maybe the most unsettling, example of this is the double-slit experiment. The setup is simple. A barrier with two thin slits, a device that fires electrons one at a time on one side, and a detector screen on the other. If you close one slit, the electrons act like tiny marbles, hitting the screen in a tight cluster right behind the open slit. Same thing if you close the other slit. No surprises. But here's where reality gets weird. When you open both slits and fire the electrons one by one, you don't get two clusters. You get an interference pattern, a series of bright and dark bands. This is a pattern that can only be made if a wave passes through both slits at once and interferes with itself. But we're firing single electrons. It's as if each electron, all by itself, travels through both slits simultaneously like a wave, interferes with itself, and then lands on the screen as a single particle. This is the core mystery of quantum mechanics. A particle can exist in multiple possibilities at once, a superposition, only to snap into a single state when it's measured. The very act of looking to see which slit the electron went through forces it to choose a path and act like a particle, which makes the interference pattern vanish. This was bizarre enough, but the physicist John Archibald Wheeler took it a step further. He came up with a thought experiment, now a real experiment, called the delayed choice experiment. Imagine the same setup, but with a twist. We decide whether to check which path the photon took or to just look at the final pattern after the photon has already passed the slits. Think about that. The photon is past the point of no return. Its past behavior, whether it acted like a particle or a wave, should be a settled fact. But that's not what happens. If we decide at the last second to put detectors at the slits, it turns out the photon always behaved like a particle and went through just one. If we decide to remove them and look at the screen, it turns out the photon always behaved like a wave and went through both. The choice we make in the present seems inextricably linked to the reality of the photon's past. It's not so much that the future changes the past, but that the past doesn't seem to have a single, definite reality until we make a measurement in the future. It's as if the universe refuses to commit to a history until we force its hand. Wheeler described this with a cosmic analogy. Light from a quasar billions of light years away is bent by a galaxy, giving a photon two possible paths to Earth. We, here and now, can choose to either see which path it took, a particle, or combine the light to see an interference pattern, a wave. Our choice today seems connected to a path a photon took billions of years ago. This is the first crack in our ordered reality. The neat, linear progression from cause to effect is no longer a sure thing. At the quantum level, the distinction between cause and effect gets blurry. This idea, sometimes called retrocausality, is so counterintuitive that it feels impossible. And yet, the experiments show it. The arrow of time, at this tiny level, seems flexible. And if it's flexible at the quantum level, what happens if that idea is scaled up? What happens when the link between space and time finally snaps? The broken compass, when spacetime unravels. The delayed choice experiment reveals a startling crack in our simple notion of causality. But to understand why this crack exists, we have to turn to the other pillar of modern physics: Albert Einstein's theory of relativity. Einstein showed that space and time are two sides of the same coin, spacetime. And the laws of causality are written right into the geometry of spacetime. Think of an event, like snapping your fingers. It happens at a specific place and time. From this event, a cone of influence expands out at the speed of light. This is called the future light cone. According to relativity, any effect from that snap must be inside this cone, because nothing can travel faster than light. Likewise, all the causes of the snap must lie in the past light cone. Events outside these cones, in a region called elsewhere, are causally disconnected from you. This light cone structure is the universe's ultimate traffic law. It's what stops a star in another galaxy from suddenly affecting you right now. It enforces the rule that causes must happen before their effects. Causality here isn't just an idea. It's a geometric property of spacetime. But this elegant structure depends completely on space and time being inseparable. So what happens if we do a thought experiment and pull them apart? The whole structure of reality, and causality with it, unravels. Let's imagine scenario A. A universe with asterisk time, but no space. Asterisk. Everything exists at a single point. There's no here or there, only now and then. Imagine two cars on a collision course. In our world, we can see their paths and predict the crash. But in a world without space, both cars occupy the same point. They collide when their temporal paths intersect. But how could you tell a collision from two cars just passing through each other? Without space to separate them and define their interaction, the causal link becomes meaningless. Now, consider the even weirder scenario B. A universe with asterisk space, but no time. Asterisk. Here, everything exists at once. There's no before or after, just a frozen, static now. The entire timeline of the universe exists as a single sculpture. The rock is in the thrower's hand, in midair, and in shattered pieces on the floor, all at once. In a timeless universe, there is no sequence of events. And without a sequence, how can you possibly say one thing caused another? The designation of cause and effect would become totally arbitrary. You can't say throwing the rock caused the glass to break if the throwing and the breaking are part of the same eternal moment. The very foundation of causation that causes come before effects is erased. This is the deeper terror physics forces us to consider. Our sense of cause and effect is an emergent property of a universe with both space and time. The light cone that protects us from paradoxes needs both space, for the concept of speed, and time, for future and past. Remove one, and the rules vanish. Relativity adds one last dizzying twist. Simultaneity is relative. Observers moving at different speeds can disagree on whether two distant events happened at the same time. If causality were based only on the order of time, then you and I could literally disagree on which event was the cause and which was the effect. But the unified structure of spacetime saves us. It ensures that while we may disagree on timing, we will always agree on the asterisk causal order of events inside our light cones. But this protection is fragile. It hinges on space and time being bound together. The quantum world showed us the arrow of time can be bent. Relativity shows us that, in theory, severing space from time would shatter it completely. Life in the echo chamber, the nightmare unveiled. We've looked at the cracks in physics and the theoretical collapse of order. Now, let's take a creative leap. Physics doesn't suggest that quantum weirdness scales up to our everyday world. But just for the sake of argument, what if it did? What if we woke up tomorrow in a world where cause and effect was no longer a rule? It wouldn't just be chaotic, it would be a world of deep, existential horror. First, your own identity would collapse. You are a product of your memories. But what is memory in a world where an effect can precede its cause? You might remember a picnic that hasn't happened yet. You might feel the sharp pain of a cut a full minute before the knife slips. Your mind would be flooded with these informational ghosts, echoes from the future and apparitions of a past that might never have been. If your future choices can rewrite your past experiences, your identity would lose all stability. You wouldn't be a person. You'd be a collection of disconnected states. Next, we'd have to face the death of free will. We already struggle with the idea that our choices might be determined by past events. But retrocausality is far more sinister. It's not just your past determining your future, it's your future determining your past. Imagine you decide to turn left. But what if the urge to turn left was caused by something that will happen an hour later because you turned left? Did you really choose? Or were you a puppet pulled by strings stretching from both the past and the future? Choice becomes an illusion, not because you're a cog in a machine moving forward, but because you're a thread in a tapestry that's already woven from beginning to end and back again. Finally, just picture the sheer anarchy. You hear a scream, and seconds later, you see the accident that caused it. You feel full before you've even eaten. A building might crumble, and the earthquake strikes the next day. How could a society function? How can you build a house if the nails might fall out before you hammer them in? The universe would become a nonsensical, unpredictable nightmare. It would be a reality without a story, where the question, why, has no answer. Before we pull back from this fictional abyss, I have to ask, what aspect of this broken reality do you find the most terrifying? The loss of identity, the death of free will, or the pure, unlivable chaos of it all? Let me know your thoughts in the comments. The grand illusion? Okay, let's take a breath and pull back to the world we actually live in. The coffee in your cup won't get hotter on its own. The past, for all intents and purposes, is fixed. Our macroscopic world runs with the comforting reliability of cause and effect. The second law of thermodynamics holds firm, and the arrow of time points forward. So, are these quantum paradoxes just weird quirks, confined to the subatomic world and theoretical blackboards? Perhaps. But some physicists are exploring an even more radical idea, one that turns this entire problem on its head. We've been talking about causality as something that happens within spacetime. But what if spacetime itself isn't fundamental? What if it emerges from something deeper? One of the most fascinating, though still speculative, ideas is called causal set theory. It suggests that the most fundamental reality isn't a smooth canvas of space and time, but a discrete set of basic events. The only thing connecting these events is a web of pure causal relationships, a simple set of rules stating which events can influence which others. From this foundational network of cause and effect, the very fabric of spacetime and its geometry are thought to emerge. From this perspective, space and time aren't the stage where causality happens, they are the performance. The reason our universe has a coherent causal structure is because the universe is a causal structure. The arrow of time we experience might just be a statistical consequence of countless quantum causal links, solidifying at our large scale, much like the smoothness of water emerges from the jostling of individual H2O molecules. This leaves us with a final, dizzying question. We started by fearing a world without cause and effect, but maybe that's the wrong fear. Perhaps the real question is whether the order we perceive is a feature of the universe itself, or a feature of our perception. Is the reality we cherish just a shadow of something far stranger and more profound? The questions remain, right at the very edge of what we know. And the universe, for now, is keeping its secrets. Light speed is the glue holding your universe together. Imagine you could race a beam of light. Your common sense, the gut feeling that gets us through the day, tells you that the faster you go, the closer you should get. Right? The speed difference between you and that shimmering pulse of energy ought to shrink. If you're in a car doing 60, and the car ahead is doing 70, you're closing the gap at 10 miles per hour. Simple. Obvious. But what if I told you that with light, this basic rule of reality completely shatters? What if, no matter how fast you fly 90% of the speed of light, 99.9%, 99,999%, that beam of light you're chasing will always be racing away from you at the exact same, unbreakable speed? 299,792, 458 meters per second. That sounds impossible. It feels like a glitch in the code of reality, a paradox that should unravel the very logic of the cosmos. It breaks the rules of motion we've all intuitively understood since we learned to walk. But this isn't a flaw in the universe. It's not a bug. It's a clue. It's the single most important clue we have ever found about the true nature of reality. And following it, unraveling this beautiful, defiant impossibility, doesn't lead to a contradiction. It leads to a revelation so profound it forces us to abandon our most cherished ideas about existence itself. It reveals that the speed of light isn't just a number, or some ultimate speed limit we can never hit. It's something much, much more fundamental. It's the glue holding your reality together. Today, we're not just going to talk about how fast light is. We're going to understand why its speed is the law that space and time themselves are forced to obey. The world of common sense. Before we can appreciate just how weird light is, we need to get our footing in the world that makes perfect sense to us. The world of Isaac Newton, of thrown baseballs and moving trains. This is the world of Galilean relativity, and it runs on one simple idea. Speeds add and subtract exactly like you'd think. Imagine you're at a train station. A train zips by at a steady 100 kilometers per hour. Inside that train, someone starts walking toward the front at a lazy 5 kilometers per hour. From your perspective, standing on the platform, how fast is that person moving? Your brain does the math instantly. You add the train speed to the walker's speed. 100 plus 5 equals 105 kilometers per hour. And you'd be absolutely right. Now, what if that person turns around and walks toward the back of the train at the same speed? Again, the math is easy. 100 minus 5 is 95 kilometers per hour. What if they throw a baseball forward at 50 kilometers per hour? Same logic. 100 plus 50, and it's flying at 150 kilometers per hour relative to you. If they throw it backward, 100 minus 50, it's 50. This is the bedrock of classical mechanics. It's intuitive, it's predictable, and it works perfectly for everything in our daily lives. This view of the universe assumes that space is a huge, unchanging stage. A meter is always a meter, no matter where it is or how fast it's moving. And time? In this model, time is a universal clock. An unstoppable river, flowing at the same rate for everyone and everything in the cosmos. A second on my watch is a second on your watch, no matter what. My now is the same as your now. Space is the absolute arena, time is the absolute metronome. They are separate things. For over 200 years, this was the universe as we understood it. A grand, clockwork machine that was perfectly logical and totally reliable. Until a crack appeared in its foundation. A crack that came not from studying moving objects, but from studying light itself. The crack in the foundation. In the mid-1800s, a Scottish physicist named James Clerk Maxwell was messing around with what seemed like a totally different problem. He was trying to unite electricity and magnetism. And with 4 beautifully elegant equations, he did it. He showed they were just 2 sides of the same coin, electromagnetism. But buried in his math was a wild prediction. The equation said that a wave in this electromagnetic field would travel through empty space at a very specific speed. When Maxwell calculated that speed, he got a number around 300,000 kilometers per second. That number looked awfully familiar. It was the measured speed of light. In a flash of genius, Maxwell had discovered what light really is, an electromagnetic wave. But in doing so, he had accidentally created one of the biggest paradoxes in the history of science. Think back to our train. The speed of the baseball depends on who's measuring it, right? To the person on the train, it's 50. To the person on the platform, it's 150. Speeds are relative. But Maxwell's equations were different. They didn't say light traveled at speed c relative to its source. They just said the speed of light is c. Period. A constant. Fixed. Absolute. This flew in the face of everything Newton and Galileo had taught us. It just didn't make any sense. A constant speed relative to asterisk what? Scientists scrambled for an answer. The most popular idea was that there must be some invisible, undetectable stuff filling all of space, which they called the luminiferous ether. Just like sound needs air to travel, they figured light needed the ether. If that was true, then the speed of light would be constant relative to the ether. This was an idea you could actually test. The Earth is hurtling around the Sun at about 30 kilometers per second. If the ether was just sitting still, then as we plow through it, we should feel an ether wind. And that wind should mess with the speed of light. A beam of light going with the wind should move a tiny bit faster, and a beam going against it should be a bit slower. In 1887, 2 American physicists, Albert Michelson and Edward Morley, set out to find this ether wind. They built an incredibly clever device that split a beam of light, sent the 2 halves on round trips in different directions, and then brought them back together. If one beam was slowed down by the ether wind even slightly, they'd be out of sync and create a specific pattern. They set up their experiment, floating the whole thing on a pool of mercury so they could spin it around. They checked everything with painstaking precision. And they turned it on. And they found absolutely nothing. No matter how they turned the device, no matter what time of day or year they tried, the result was always the same. Nothing. There was no ether wind. The speed of light was stubbornly, defiantly, the same in every direction. This experiment, famously called the most important failure in history, created a huge crisis in physics. The rules were at war with each other. On one side, you had centuries of common sense that said speeds have to add and subtract. On the other, you had Maxwell's math and this new experiment insisting that the speed of light was an absolute constant. One of them had to be wrong. The entire building of physics was teetering, waiting for someone to either find the flaw in the experiment or, if they were brave enough, to tear down the old foundation and build something completely new. Einstein's audacious leap. The person who dared to tear it all down wasn't some big-shot professor. He was a young patent clerk in Bern, Switzerland. His name was Albert Einstein. For years, Einstein had been obsessed with this paradox. He'd been thinking about it since he was a teenager, famously wondering what it would be like to ride on a beam of light. Would the wave be frozen next to you? Maxwell's equation said no way, that's impossible. But common sense said it should be. Most physicists were trying to save the old rules. They came up with all sorts of complicated patches, like maybe the Earth dragged the ether along with it. But these were just desperate fixes trying to prop up a failing system. Einstein took a totally different path. He decided to just trust the evidence. All of it. He looked at the two warring ideas and made a bold choice. Instead of questioning the weirdness of light, he decided to question space and time themselves. In 1905, he published his theory of special relativity, built on two simple, elegant ideas. First, the principle of relativity. He said the laws of physics are the same for everyone who's moving at a constant speed. This means there's no special, at-rest spot in the universe. If you're in a smoothly moving, windowless train car, there's no experiment you can do to prove you're moving. All motion is relative. His second idea was the radical one. He took the bizarre result from the Michelson-Morley experiment and just declared it a fundamental law of nature. The speed of light in a vacuum, see, is the same for everybody, no matter how fast they're moving. Think about how brave that is. Everyone before him assumed space and time were the absolute, rigid constants. Einstein flipped that completely on its head. He declared that the speed of light was the one true, unshakable constant. And if the speed of light is absolute, then space and time have to be flexible. They have to be relative. He was saying that if our stopwatches and our rulers give us answers that contradict the constant speed of light, then it's our stopwatches and rulers that are wrong. The universe, to protect this one cosmic law, must be willing to literally stretch time and shrink space. This was the turning point. By making light the king of the cosmos, Einstein had demoted space and time to be its obedient subjects. He didn't just patch the crack in the foundation of physics, he laid a brand new one. And from this new foundation, a universe far stranger and more wonderful than anyone had ever imagined would begin to emerge. The consequences. Part 1 times elasticity. To really get what Einstein did, let's build one of his favorite thought experiments, a light clock. Imagine a simple clock made of two mirrors, with a single particle of light, a photon, bouncing between them. Every time the photon hits the bottom mirror, the clock ticks. Let's say the mirrors are about 300,000 kilometers apart. The photon goes up, hits the top mirror, comes back down. The round trip is 600,000 kilometers. Since light travels at 300,000 kilometers per second, this round trip takes exactly 2 seconds. Tick. Tock. Now, let's put this clock on a spaceship. You're inside the ship, so from your perspective, nothing has changed. The photon is still just going straight up and down. The clock still ticks every 2 seconds. This is Einstein's first rule in action. The laws of physics are the same for you in your moving ship. But now, let's watch your spaceship and its light clock fly past us at, say, 80% of the speed of light. From our stationary point of view on Earth, we see something very different. We see the clock moving sideways. So for us, the photon doesn't travel a straight up and down path. It has to travel a longer, diagonal path to catch up with the top mirror. Then it travels another long, diagonal path to get back to the bottom mirror, which has moved even further. And here's the mind-bending part. We see the photon travel a longer distance than you do on the ship. And this is the rule we absolutely cannot break. Einstein's second idea demands that we both must measure the speed of that single photon to be exactly the same. How is that possible? If speed is the same for both of us, but we see the photon travel a longer distance, how can the math work? The only way the equation "speed equals distance, time" can hold true is if the "time" part of the equation changes for you. Since the distance is longer from our perspective, the time it takes for your clock to tick must also be longer from our perspective. Your tick and tock are taking more time from our point of view. From where we stand, your clock is running slow. This isn't an illusion. It's a real, physical effect called time dilation. To protect the constant speed of light, the universe literally slows down your time relative to ours. The faster you move through space, the slower you move through time. This has been proven beyond any doubt. High in our atmosphere, cosmic rays create unstable particles called muons. At rest, muons decay in just 2 microseconds. Even traveling near the speed of light, they should only last long enough to travel a few hundred meters, so we shouldn't see them down here on the ground. But we do. We detect them all the time. Why? Because these muons are traveling at about 99.8% the speed of light. At that speed, their internal clocks are slowed down from our perspective by a factor of about 15. This stretched-out lifetime gives them more than enough time to reach the surface. The muons are tiny, living clocks proving that time really does stretch. This leads to the famous twin paradox. If one twin leaves Earth on a high-speed journey and comes back, she will be younger than the twin who stayed home. The paradox is resolved because to come home, the traveling twin has to slow down, turn around, and speed up again. She's the one who feels the acceleration, and she's the one who will be younger upon return. Time isn't a rigid, universal river. It's personal and elastic, flowing at different rates for different people. And the one thing that dictates its flow is the one true constant: the speed of light. The consequence is Part 2: space's malleability. Okay, so time has to stretch to protect the cosmic speed limit. But time is tied to space. If time has to be flexible, then space has to be just as flexible. They're partners in a cosmic dance. When one moves, the other has to react. Let's go back to your trip to that star 4 light years away. We, on Earth, agree the distance is 4 light years. We see you travel at 80% the speed of light, 0.8 and we calculate that your journey takes 5 years. For us, it all adds up. Distance, 4 light years, equals speed, 0.8 x time, 5 years. Now let's jump into your shoes on the spaceship. We already know you only experience 3 years passing. But you also agree on your speed. You see the star approaching you at 0.8 So both you and the observers on Earth agree on the relative speed. But now there's a problem from your point of view. If your speed is 0.8 and your travel time is only 3 years, what distance have you traveled? Well, speed times time is distance. 0.8 times 3 years is 4 light years. Wait, what? How can the distance to the star be 4 light years for people on Earth, but only 4 light years for you? The answer is just as profound as time dilation. Just as the universe slows your time, it also shrinks space for you. This is called length contraction. From your perspective on the ship, the entire universe in the direction you're moving has been squished. The distance from Earth to that star, which we on Earth measure to be 4 light years, has physically shrunk to a length of 4 light years in your reference frame. This isn't an optical illusion. The space itself has contracted. The universe literally alters its own dimensions to make sure that you, in your frame of reference, still measure the speed of light to be c. We see this happen in particle accelerators all the time. Heavy ions, which are spheres when they're at rest, are observed to flatten into pancakes when they're accelerated to near light speed, a perfect confirmation of this spatial shrinking. Think back to the muons. From our perspective on Earth, the muon survives its journey because its time slowed down. But what about from the muon's perspective? In its reference frame, its own lifespan is the normal 2 microseconds. It isn't experiencing time dilation for itself. So how does it reach the ground? From the muon's point of view, the Earth's atmosphere is rushing up to meet it at 99.8% the speed of light. Because of this incredible speed, the whole atmosphere, which is about 10 kilometers thick for us, is length contracted from the muon's perspective to be only a few hundred meters thick. A journey of a few hundred meters is no problem in 2 microseconds. So, we say the muon made it because its time stretched. The muon says it made it because our space shrank. Two completely different explanations for reality. And both are correct. Both perfectly explain what we see. And both are necessary consequences of one single, unwavering fact. The speed of light is constant for everyone. The grand synthesis, spacetime, the glue. So, we've seen that time can stretch and space can shrink. But these aren't just a collection of weird party tricks that happen at high speeds. They're clues pointing to a much deeper reality. They're proof that space and time aren't separate things at all. Imagine you're holding a ruler. You can describe its length by how it lines up with the dimensions of a room. How much is along the x-axis? How much along the y-axis? If you rotate the ruler, those numbers change. The x part might get shorter while the y part gets longer. But the actual, physical length of the ruler itself doesn't change. It's constant. It's invariant. Einstein realized that moving through space is a kind of rotation. Not through space, but through a higher, four-dimensional reality that fuses space and time together. He called it spacetime. In this new picture, everything has a location in 4 dimensions. The 3 dimensions of space, length, width, height, and the 1 dimension of time. An event isn't just a place, it's a place and a time. And here is the most beautiful, mind-bending part of this whole story. Every single object in the universe is constantly moving through this 4-dimensional spacetime at exactly 1 speed asterisk. The speed of light. That's right. You, sitting there right now, are traveling at the speed of light. How can that be? Well, your motion is split between the dimensions of space and the dimension of time. When you're sitting still, in space, all of your light speed travel is dedicated to moving through the time dimension. 100% of your motion is just experiencing time flowing forward. The moment you start to move through space, you begin to rotate in space-time. You divert some of your motion from the time dimension into the space dimensions. The faster you go through space, the more of your light speed motion is used for that, and the less is left over for your journey through time. As a result, your time slows down compared to someone who is more at rest. If you could reach the speed of light in space, you would have diverted all of your motion into the spatial dimensions. Your entire light speed journey would be through space, leaving 0 for your journey through time. Your time would stop completely. A photon, which travels at c, experiences no time at all. From a photon's point of view, the moment it's created and the moment it's absorbed happen at the exact same instant. This is the real meaning of time dilation and length contraction. They're just shadows of a deeper reality. They're what happens when we try to measure this 4-dimensional world using our separate ideas of space and time. The speed of light, then, isn't just a speed limit. It is the fundamental conversion factor between space and time. It's the rule that tells the universe how much time is equivalent to how much space. It is the very thing that stitches them together into a single, dynamic fabric. Without that constant, space and time would fall apart into Newton's old, separate, and incorrect model. C is the thread that holds it all together. It's the glue. If realizing that you're currently traveling at the speed of light is starting to reshape your picture of reality, then you know what to do. Hit that subscribe button and ring the bell, because this journey into the fabric of the cosmos only gets deeper from here. The ultimate limit, causality. So we know space and time will bend and warp in incredible ways to stop anything with mass from ever reaching the speed of light. It would take an infinite amount of energy, which is impossible. But let's just ask one last, what if? What if you could break that rule? What if you could send a signal, or anything, faster than light? What would actually break? The answer isn't just a law of physics. The answer is logic itself. What breaks is causality. Causality is the simple, fundamental rule that a cause must always come before its effect. You drop a glass, then it shatters. You flip a switch, then the light turns on. This is the arrow of time, the foundation of a rational universe. The speed of light, c, isn't just the speed of photons. It is the asterisk speed of causality. It is the maximum speed at which any cause can ripple through spacetime to create an effect. Here's why. One of the weirdest results of relativity is that people moving at different speeds can disagree on the order of two events. And this is key, they can only disagree if the events are so far apart that light couldn't have traveled from one to the other. But if you could send a signal faster than light, you could create a situation where the order of a cause and its effect becomes reversible. Imagine there's a planet 1 light-year away. I build a faster than light, FTL, transmitter and send a message. Explode. Let's say the signal travels at twice the speed of light. In 6 months, the planet explodes. From my point of view, cause came before effect. I sent the message, then it blew up. Now, you come flying past me in a spaceship at nearly the speed of light. Because of the relativity of simultaneity, from your point of view, you could see the planet exploding first. And then, 6 months later from your perspective, you would see my signal arriving back at my transmitter at the exact moment I sent it. In your perfectly valid, physically real frame of reference, the effect happened before the cause. It gets worse. In theory, you could use this to create an impossible paradox. You could send a signal back in time to stop your own grandfather from meeting your grandmother. But if you succeed, you were never born to send the signal in the first place. But if you never sent the signal, you were born, which means you could send the signal. And the universe gets trapped in a loop of pure contradiction. The speed limit, c, is the universe's ultimate firewall. It's a structural property of spacetime that protects its own logical integrity. It prevents the past from being changed and ensures that before always comes before after. Breaking the speed of light doesn't just mean going fast, it means breaking the timeline itself. We started with a simple question. What happens when you try to race a beam of light? We thought we were asking about speed, but we were really asking about the nature of existence itself. The answer is that the universe rearranges itself. It stretches the second and shrinks the meter. It does this not to be difficult, but to uphold a far more profound law. The constancy of light's speed is the foundation on which our reality is built. It's the rule that forces space and time to give up their independence and merge into a single fabric, spacetime. It dictates that all of us are on a perpetual journey through this four-dimensional world at light speed, trading motion through time for motion through space. And finally, it stands guard over logic, protecting the sacred order of cause and effect. The speed of light isn't a barrier. It's the fundamental symmetry of our universe. It is the weaver, the guardian, and the glue. So the next time you look up at the night sky and see the faint twinkle of a distant star, remember what you're really seeing. That ancient light hasn't just been traveling through the vast emptiness of space for millions of years. For that entire journey, it has been carrying the fundamental secret of the cosmos. The law that binds our universe together. The glitch that proves spacetime isn't real. Modern physics, pretty much all of it, is built on two of the most brilliant ideas humanity has ever had. The first is Einstein's general relativity. It tells us that time is a bit like silly putty, a flexible, dynamic dimension that bends and stretches with gravity. The second is quantum mechanics, the mind-blowingly successful theory of the very small, which treats time more like a universal metronome, ticking at the same rate for everything, everywhere. These two theories are the bedrock of our universe. They've been tested and proven to an absurd degree of precision. There's just one tiny problem. They are fundamentally, dramatically incompatible. When it comes to the nature of time, they cannot both be right. This one, single conflict creates a deep glitch in our description of reality. It's a crack in the very foundation of physics that suggests the unified spacetime we all experience isn't fundamental. It's an illusion. And hiding at the heart of that illusion, behind every tick of every clock, is maybe the deepest secret of the cosmos. The true, and truly bizarre, nature of time. To find it, we first have to get our heads around the two conflicting realities that physics is showing us. Part 1. The flawless machine, the problem. Einstein's perfect spacetime. For most of human history, time was simple. It was Isaac Newton's clock. A single, grand metronome for the entire universe, ticking away at a constant, absolute rate, no matter what. Every corner of the cosmos was thought to be perfectly synchronized to this one, true time. It was simple, elegant, deeply intuitive. And completely wrong. In the early 20th century, a young patent clerk named Albert Einstein completely shattered this idea. With his theory of special relativity, he showed that time isn't absolute. It's relative. The rate at which time passes for you literally depends on how fast you're moving. Imagine a train zipping down a track. If lightning strikes the front and back of the train at the exact same moment for someone standing on the platform, a passenger on that train would actually see the lightning hit the front before it hits the back. So, who's right? According to Einstein, they both are. There's no such thing as a universal, now. But that was just the warm-up. A decade later, with his theory of general relativity, Einstein dropped an even bigger bombshell. Gravity, he said, isn't a force. It's a curve in reality itself. He asked us to picture spacetime as a single, four-dimensional fabric, kind of like a huge, stretched-out trampoline. A massive object like the sun creates a deep dent in this fabric. Planets like Earth aren't being pulled by the sun. They're just rolling along the straightest possible path in that curved space. As the famous saying goes, matter tells spacetime how to curve, and curved spacetime tells matter how to move. This curvature doesn't just affect space, it affects time. Time actually flows more slowly in a strong gravitational field. A clock on the beach will tick just a tiny bit slower than a clock on a mountaintop. A clock near a black hole would tick dramatically slower. This isn't a mechanical problem. It's how the universe works. Time is woven into the very fabric of space. You can't have one without the other. They are a single, dynamic thing, spacetime. In Einstein's world, reality is a smooth, continuous, and flawless machine. The quantum clock. At the exact same time Einstein was dreaming up his cosmic trampoline, another revolution was kicking off. Quantum mechanics, the science of the super-small. And if Einstein's universe is a smooth, flowing river, the quantum universe is a pixelated, jittery world of pure chance. Down here, things aren't definite. Particles can be in multiple places at once, in a state called superposition. They can be mysteriously linked across galaxies through something called entanglement. And, most importantly, energy isn't continuous. It comes in little packets, or quanta. You can have one quantum of energy, or two, but never 1.5. Everything is chunky. So how does this famously weird theory handle time? Well, in total contrast to Einstein's flexible spacetime, standard quantum mechanics treats time as something separate and absolute. It's a rigid background ruler that the weird quantum drama unfolds against. Think of it like the frames of a movie. Quantum mechanics can tell you the state of all the particles on each individual frame. The jump from one frame to the next is handled by the Schrödinger equation. But the time that moves the frames forward isn't part of the movie. It's more like the sprockets on the film reel, an external, universal clock that's completely unaffected by anything happening in the film itself. In the quantum world, space is where things are, and time is just when they evolve. They're treated as fundamentally different things, using totally different math. And for almost a century, these two ideas, relativity and quantum mechanics, have stood apart, each ruling its own kingdom with breathtaking accuracy. But what happens when their kingdoms overlap? What happens when you need to describe something both incredibly massive and incredibly small? This is where the flawless machines crash into each other. Part 2. The glitch in the code, the agitation. The crash. There are places in our universe where these two great theories have to meet. Inside a black hole, and at the very beginning of the Big Bang. These are places with immense gravity, where spacetime is stretched to its breaking point, but they're also so small that they have to follow quantum rules. To describe them, we need a theory of quantum gravity. And for 100 years, the search for that theory has been haunted by one major problem: the problem of time. The conflict hits you right away. General relativity says space-time is a smooth, continuous sheet. But quantum mechanics insists that at the smallest scales, everything is quantized, or chunky. So if that's true, space-time itself must be quantized. It can't be a smooth fabric. It must be more like a pixelated grid, woven from indivisible units of space and time at the tiniest possible scale, the Planck length. At this scale, the beautiful equations of general relativity just break. They start spitting out infinities, which is a big red flag in physics. The smooth fabric of spacetime tears apart. It's a sign that the two theories are speaking fundamentally different languages about reality. The most dramatic sign of this crash is what happens to time itself. When physicists like John Wheeler and Bryce DeWitt first tried to combine the two theories into a single equation, they created the infamous Wheeler-DeWitt equation. This equation was supposed to describe the quantum state of the entire universe. But it had a bizarre, deeply unsettling feature. The variable for time was completely gone. According to this equation, if you could look at the universe as a whole quantum system, it doesn't evolve. It's static, frozen, timeless. This shocking result is known as the problem of time. An equation designed to describe everything happening in the cosmos was instead suggesting that, at the most fundamental level, change itself might be an illusion. The glitch was found. The universe's clock wasn't just broken, it seemed to be missing. The unsettling consequences. What does it even mean for reality if time doesn't exist at a fundamental level? It means the basic principles we use to make sense of the world start to wobble. First, causality gets weird. Our whole lives are built on cause and effect. This happens, which causes that to happen. But that logical chain requires a clear before and after. Without a master clock to put events in order, the very idea of a cause coming before its effect starts to get fuzzy at the quantum level. Second, our idea of locality shatters. Relativity is built on the rule that nothing can travel faster than light. An event can only be affected by its immediate surroundings. But quantum entanglement seems to laugh at this. You can link two particles so that measuring one instantly influences the other, even if they're on opposite sides of the galaxy. Einstein famously called this spooky action at a distance. It's important to clarify, this doesn't mean you can send messages faster than light. Causality is safe. But it does challenge our sense of separation, suggesting the universe is connected in a way that goes deeper than the space between things. But the most important consequence for us is the breakdown of quantum coherence. This is the key to why we don't see all this quantum weirdness in our daily lives. A particle can only be in a superposition multiple states at once as long as it's isolated. The moment it interacts with its environment, it snaps into a single, definite state. This is called decoherence. Think of the environment as constantly watching every particle. This observation destroys the fragile quantum states. The real difference between the quantum and classical worlds isn't size, it's information. It's about how much information about a system is leaking out into its surroundings. This process of decoherence is the glitch in action. It's the mechanism that hides the bizarre, timeless quantum reality from us, creating the illusion of the stable world we know. The chair you're sitting on feels solid and fixed because countless photons are bouncing off it and telling your eyes where it is, constantly locking in its position. Just by looking at it, you are helping to create its classical reality. This leads to a mind-blowing conclusion. The world we see isn't the real thing. It's a filtered version, one outcome selected from a sea of quantum possibilities. The glitch isn't a bug, it's a feature. It's the door between two worlds, and it suggests that time and space aren't the bedrock of existence. They are emergent shadows cast by a deeper, stranger, and ultimately timeless quantum world. Part 3. Rebooting reality, the exploration solution. Is time emergent? So if spacetime isn't fundamental, what is it? The most revolutionary idea in physics today is that spacetime is emergent. It's not the stage, it's a projection, maybe even a hologram, generated by something far more basic. To get your head around emergence, think about wetness. A single hydrogen oxide molecule isn't wet. Wetness is a property that emerges from the collective dance of trillions of molecules together. Or think about the temperature of a room. No single air molecule has a temperature. It's an emergent property of their average speed. These things don't exist at the micro level, they're macro illusions. What if time and space are like that? What if they emerge from a vast, underlying quantum system? One of the most audacious ideas is that spacetime literally emerges from quantum entanglement. This finds its clearest voice in something called the holographic principle. It suggests that a universe with gravity, like ours, could be a holographic projection of a simpler quantum system living on its distant boundary. The geometry of the space inside the hologram, the fabric of space itself, is actually encoded in the entanglement patterns of the particles on the boundary. The more entangled two particles on the boundary are, the closer together they are in the interior space. It's a wild idea, leading to the even wilder conjecture known as equals EPR. Proposed by Leonard Susskind and Juan Maldacena, this suggests that a wormhole, an bridge, might just be the geometric shape of two entangled particles, an EPR pair. In other words, two black holes entangled on opposite sides of the universe could be secretly connected by a wormhole. Space-time geometry, it seems, might literally be built from entanglement. Okay, so that's space. But what about time? Back in 1983, physicists Don Page and William Wouters proposed a way that time, too, could emerge from a timeless universe. They imagined splitting the static, frozen universe of the Wheeler-DeWitt equation into two entangled parts: a clock and the rest of the universe. For an imaginary observer outside the whole system, nothing changes. It's static. But for an observer inside who is part of the system, they would see the rest of the universe appearing to evolve relative to the state of the clock. Time, in this view, isn't a fundamental flow. It's the relationship we see unfolding between a part of the universe we call a clock and everything else. Our experience of time's passage is just us being dragged along by our entanglement with the rest of the cosmos. A universe without time, and a new way to build it. This perspective changes everything. Suddenly, the problem of time isn't a problem. The Wheeler-DeWitt equation might be telling us the literal truth. The universe as a whole is timeless, and time is just a feature of our limited point of view from the inside. But if our world emerges from quantum chaos, why is it so consistent? The answer might lie in an idea called quantum Darwinism. This theory suggests that the emergence of our objective reality is a kind of natural selection. When a system interacts with the environment, certain stable, robust quantum states called pointer states are naturally favored. The environment doesn't just select these states, it makes countless redundant copies of their information. A chair doesn't just sit there. It constantly imprints information about its position onto the photons bouncing off it and the air molecules bumping into it. This flood of identical, public information is why we all agree the chair is there. Classical reality is objective because it's redundant, it's what's left after the quantum weirdness is filtered out and the surviving information has been copied a billion times over. For decades, this has been a powerful philosophical picture, but the core mathematical mismatch remained. That is, until very recently. New approaches in quantum foundations are starting to heal this century-old schism. Instead of treating space and time differently, some physicists are developing frameworks that can describe a system's entire history as a single, holistic quantum object. This would allow quantum correlations across both space and time to be described with the exact same mathematical language for the first time. This doesn't mean we have a full theory of quantum gravity. Not yet. But it's a huge step. It suggests the glitch was never in the universe, but in our description of it. Spacetime isn't broken. It just wasn't the beginning of the story. This whole journey, from a clock on the wall to the edge of a timeless reality, is one of the greatest adventures we're on. It forces us to question everything we take for granted. If this trip into the illusion of spacetime has reshaped how you see the world, let me know. And I have to ask, after all this, do you think time is a fundamental part of the universe, or is it the grandest illusion of them all? Drop your thoughts in the comments below. We started with two perfect theories: Einstein's universe of smooth, flowing spacetime, and the quantum world of jittery probabilities ticking to an absolute beat. We found that where they meet, they don't just disagree, they break down. This glitch led us down a rabbit hole where the solid world we know became an illusion, projected from a chaotic quantum reality. And most profoundly, we found that spacetime itself, the very stage of our lives, might not be fundamental at all. It seems to be an emergent hologram, woven from the threads of quantum entanglement. The distance between 2 points may just be a measure of how weakly they are entangled. The passage of a second may be nothing more than the unfolding of correlations within a timeless whole. It now seems the universe doesn't have a clock. In a very real sense, the universe is the clock. Every particle, every interaction, every entangled pair contributes to the grand, collective illusion we call spacetime. The reality we live in is a ghost in the machine, a phantom emerging from a deeper, spaceless, and timeless quantum world. So the next time you look at a clock, watching the seconds tick by, remember what you're really seeing. You're not just measuring a simple, forward march. You are witnessing the breathtaking result of countless quantum connections, an echo of a reality so strange it has no space, no past, and no future. You're seeing the glitch that proves spacetime isn't real. The cosmic glitch that would erase reality. There are rules that govern our world. Unseen, unfelt, but totally absolute. The rule that says gravity pulls you down, not up. The rule that you can't be in two places at once. But underneath all of these is a master rule, a single piece of cosmic architecture so fundamental that without it, the universe as we know it simply couldn't exist. It's a pact, a fusion, a bond between two ideas we take for granted: space and time. We live our lives on a stage built from these two things. Space is the where. Time is the when. They feel separate, don't they? Like the x and y axes on a graph. You can move through space, from your home to work, while time just sort of moves you along, from this morning to this evening. It feels simple, safe, and intuitive. But what if that separation is just an illusion our brains cook up to keep us sane? What if the stage itself isn't just wood and paint, but a single, interwoven fabric? And what if there was a glitch? A fundamental error in the code of existence that could tear that fabric apart. This isn't a story about monsters or aliens. This is a story about a far greater horror. The ultimate cosmic error, a glitch that would unravel not just our future, but the very meaning of our past, and erase reality itself. The unseen foundation of everything. Before we can break the universe, we have to understand what holds it together. For most of human history, our model of the cosmos was simple and elegant, thanks in large part to Isaac Newton. In his clockwork universe, space was an infinite, unchanging, three-dimensional grid. It was the absolute stage. A meter was always a meter, whether you were on Earth or on Mars, standing still or sprinting. It was rigid and reliable. And then there was time. For Newton, time was a universal river, flowing at the exact same rate for everyone, everywhere. A second on your watch was a second for a distant star. It was a single, shared metronome for all of existence. Space was the where, time was the when, and the two had nothing to do with each other. This worldview is hardwired into us. It just feels right. It's the reality our brains evolved to handle. But in the early 20th century, a young patent clerk in Bern, Switzerland, started obsessing over a contradiction, a single loose thread that, when pulled, would unravel Newton's entire beautiful tapestry. His name was Albert Einstein, and the thread was the speed of light. Physicists had figured out that light travels at a very specific, very finite speed. Roughly 792 kilometers per second. But here's the bizarre part. The math showed that this speed was constant for everyone. This is where your intuition hits a brick wall. Imagine you're on a train going 100 kilometers per hour, and you throw a ball forward at 20 kilometers per hour. For someone on the platform, the ball is moving at 120 kilometers per hour. Speeds add up. Simple. But if you're on that same train and you turn on a flashlight, something impossible happens. The light races away from you at the speed of light. But for the observer on the platform watching you fly by, that same beam of light is also moving at the exact same speed of light. Not the speed of light plus the speed of the train. Just the speed of light. This paradox is what kept Einstein up at night. How could light's speed be absolute for everyone, no matter how they were moving? It seemed logically impossible. Something had to give. Either the laws of physics weren't the same for everyone, or our basic understanding of space and time was fundamentally wrong. Einstein bet on the speed of light. He made it the one non-negotiable rule. And by doing that, he had to tear down Newton's clockwork universe. To make the math work, to solve the paradox, Einstein realized that space and time couldn't be separate and absolute. They had to be flexible. They had to be interwoven into a single, unified, four-dimensional continuum, spacetime. Think of it not as a rigid grid, but as a stretchy, malleable fabric. This isn't just a fun analogy, it's the heart of his theory of special relativity. Your motion through space directly affects your journey through time. The faster you move through space, the slower you move through time relative to a stationary observer. This isn't your clock just ticking slower, it's asterisk time itself slowing down for you. At the same time, objects in motion actually shrink in their direction of travel. This is the hidden architectural requirement of our universe. Space and time must be able to stretch, shrink, and warp, all to preserve that one unbreakable law. The speed of light is constant for everyone. They aren't two separate things, they are two faces of the same coin. This fusion is what holds reality together. It's what ensures that cause comes before effect and that the universe has a coherent story. And now, we're going to break it. The glitch and the unraveling. Let's imagine the unimaginable. A glitch. Not an explosion, but a quiet change in the universe's source code. The pact is broken. The fusion is severed. Space and time are now separate, independent things, just like Newton imagined. Space is a static grid. Time is a universal clock. At first, maybe nothing seems to happen. The Earth is still orbiting the Sun. Life goes on. But the foundational logic of the cosmos has been corrupted. The fail-safe is gone. And the first, most immediate, and most horrifying consequence begins to unfold. the complete breakdown of past, present, and future. In our universe, the flow of time creates sequence. It's what separates before from now, and now from after. But in our glitched universe, time is no longer a path you travel along. It's just a label. Without the fusion of space and time, there's no structure that orders events. All moments past, present, and future are no longer points on a line. They're just points. And with no line connecting them, what keeps them apart? The answer is nothing. Imagine your life is a reel of film. In a normal universe, a projector shines light through one frame at a time, creating the illusion of a story unfolding. Our glitch has just smashed the projector and laid every single frame of film on top of each other, all at once. Suddenly, you are experiencing every moment of your existence simultaneously. Your first breath, your first steps, every meal you've ever eaten, every word you've ever spoken, your final dying gasp, all of it is happening now. There is no was. There is no will be. There is only a single, deafening, eternal is. This isn't memory. It's direct, sensory experience. You feel the warmth of a childhood vacation at the same instant you feel the cold tile of a hospital floor. You taste your first kiss and the bitterness of your greatest loss in the same moment. The joy of a wedding and the grief of a funeral are not memories, they are coexisting realities. Your mind, which evolved to process a single stream of information, is now drowning in an infinite ocean of sensation. The very idea of you shatters. Who are you? The hopeful child? The burdened adult? The reflective elder? In this broken reality, you are all of them, and none of them. Your identity, a story built on memory and anticipation, dissolves into a screaming mess of a billion contradictory selves. Cause and effect becomes a meaningless joke. In our world, the cue ball hits the 8 ball, which then falls into the pocket. Sequence is guaranteed. But here, before, has no meaning. You see the glass shatter on the floor. Simultaneously, you see yourself dropping it. And you also see it sitting perfectly intact on the table. All 3 states are true at once. Which caused which? The question makes no sense. The universe is no longer a story. It is a single, static, infinitely dense collage of every event that has ever happened or will ever happen. Every birth, every death. Every star that ever ignited and every star that ever faded. The Big Bang and the final heat death of the cosmos. All of it, a frozen, screaming, simultaneous moment. The past isn't gone. The future isn't coming. Everything is now. Forever. The cosmic horror unleashed. We've seen the psychological collapse of a universe without sequence. But the true horror runs deeper. The glitch doesn't just destroy our perception of reality. It attacks the laws of physics that make reality possible in the first place. Let's start with the law that got us here, the speed of light. In Einstein's universe, it's the ultimate speed limit. But in our glitched reality, that law becomes nonsense. Speed is distance divided by time. If space and time are now totally separate, what happens to that ratio? The universal speed limit is gone. In some places, light might appear to travel infinitely fast. In others, it might grind to a halt. Particles could now outrun light. And this leads to a much more terrifying breakdown: the complete annihilation of causality. Physicists use a concept called a light cone to visualize cause and effect. It's basically the zone of the future that an event can influence. An effect must be inside the future light cone of its cause. It's a geometric law of spacetime. But what happens when the speed of light is no longer constant? The light cone dissolves. An event anywhere can now influence an event anywhere else, instantaneously. The consequences are a nightmare. An effect can now happen before its cause. A window could shatter, and a moment later, a baseball could be thrown at it. But it wouldn't be time travel. From another perspective, someone might see the ball thrown first. With no fixed order, all possibilities exist at once. The universe loses its coherent history, becoming an infinite number of contradictory stories all playing out simultaneously. And it gets worse. Let's talk about gravity. Einstein showed us that gravity isn't a force, it's the curvature of spacetime. As the physicist John Wheeler put it, matter tells spacetime how to curve, and curved spacetime tells matter how to move. It's an elegant dance. A planet orbits the sun because it's following a straight line through the curve in spacetime created by the sun's mass. Now, imagine that dance in our glitched universe. Matter tries to tell spacetime how to curve. But spacetime doesn't exist anymore. There's only space and time. Which one does it talk to? The equation, the very language of gravity, becomes gibberish. Gravity, the grand architect of galaxies, stars, and planets, just stops working. The cosmos would dissolve into a chaotic soup of directionless matter. This leads us to the final breakdown. In our universe, things like energy and momentum are conserved. Energy can't be created or destroyed, only changed in form. This isn't just a helpful rule. It's a deep truth about the universe, proven by the brilliant mathematician Emmy Noether. Noether's theorem says that because the laws of physics are the same at all times, a temporal symmetry, energy must be conserved. In our glitched universe, that symmetry is obliterated. Time is no longer smooth and continuous. By breaking the link between space and time, we've violated the conditions of Noether's theorem. Conservation of energy fails. What does that look like? It looks like pure, unpredictable magic. A star could simply vanish, its energy gone without a trace. A black hole could pop into existence from nothing. The fundamental accounting of reality is broken. There are no rules. Anything can happen. And therefore, nothing has meaning. The inevitable conclusion. What is the ultimate fate of a universe that's become a physical and logical contradiction? Describing it is tough, since our language is built on concepts that have been erased. But we can imagine two horrifying possibilities. The first is a great freeze. The universe becomes a single, static, four-dimensional crystal. It's a frozen tableau of every event that ever was or would have been, all existing simultaneously and eternally. Inside this motionless sculpture is the Big Bang, right next to a dying star. There's you as a sleeping infant, a running child, and a still corpse, all suspended in the same space, forever. There is no motion, no change, because those things require time. The universe isn't dead, it was never truly alive. Its existence reduced to a single, infinitely complex museum piece with no one to see it. The second possibility is even more terrifying: eternal chaos. Instead of freezing, the universe dissolves into a boiling, chaotic mess. Without spacetime to provide structure, particles blink in and out of existence permanently. Space itself becomes a fractured foam where distance is meaningless. To exist here would be to experience a constant, violent reshuffling of everything. One moment, you might be a person. The next, your atoms are scattered across a billion light years, or they've turned into pure energy, or they've just ceased to exist. It's a universe having a perpetual, meaningless seizure. Whichever fate befalls our broken universe, the silent crystal or the screaming foam, the outcome is the same. The utter erasure of reality as a coherent concept. It's not just the end of life or the universe. It's the end of is. The end of logic. The end of meaning. The wrap-up and lingering thought. So, we've walked through the ruins of a broken reality, all by snipping a single, hypothetical thread. The bond between space and time. We watched as it dissolved our sense of self, then unraveled the very laws of physics: causality, gravity, the conservation of energy, leaving us with a universe that was not just hostile to life, but hostile to logic itself. Now, this has been a thought experiment. As far as we know, the fusion of space and time is perfectly stable. The laws of physics hold. But the power of this cosmic horror story isn't about whether it could happen. It's about the profound truth it reveals. It forces us to see that the reality we perceive, the solid world, the steady passage of time, the comfort of cause and effect, isn't a given. It's an emergent property. It's the result of incredibly precise and interwoven rules operating far beneath our daily experience. We live inside a finely tuned machine, and we don't have the blueprints. We just take for granted that the code will keep running. This thought experiment is a chilling reminder that this stability is a gift of the cosmos. The reality we know is built on a foundation we can't see, a cosmic handshake between space and time. Breaking that handshake would erase not just our future, but our past, and the very possibility of a present. It teaches us that the greatest horror may not be a monster in the dark, but the realization that the light itself and the space and time it travels through is part of a delicate, beautiful, and terrifyingly fragile design. What if time existed but space did not? Close your eyes. Imagine a reality with no such thing as location. No here or there. No distance separating you from the farthest star. No up, no down, no inside, no outside. Now, open them. You're still you. But you have no size, no shape, and nowhere to asterisk be. You're a disembodied point of awareness, floating in an infinite, featureless void. The only thing you have left is time. A constant, unstoppable march of before and after. In a universe without the three dimensions of space, could you still think? Could you learn or remember? Could you even exist? This isn't just a philosophical brain teaser. This is a journey to the absolute bedrock of physics. By trying to imagine a universe with only one temporal dimension, we have to face some of the deepest and most startling truths about our own reality. We're about to journey into a world without dimensions to discover not only what we would lose, but to find out if anything, even time itself, could possibly remain. Tearing the fabric of reality. Before we toss space in the bin, we need to appreciate what it really is. For most of history, we've treated space and time as two totally separate things. Space was the stage, and time was the universal clock. Isaac Newton pictured space as an absolute, unmoving grid of fixed cosmic coordinate system. He believed that if you were standing still relative to that grid, you were truly at rest. Time, for him, was just as absolute, a single cosmic clock ticking at the same rate for everyone, everywhere. It was simple, intuitive, and it worked beautifully for predicting everything from falling apples to orbiting planets. Then, in 1915, Albert Einstein blew it all apart. With his theory of general relativity, he showed that space and time aren't separate at all. They're woven together into a single, four-dimensional fabric, spacetime. The classic analogy is to imagine spacetime as a huge, stretchy rubber sheet. Massive objects, like planets and stars, create dips in this sheet. What we feel as gravity isn't some mysterious force pulling us down. It's just us following the curves in space-time created by Earth's mass. As the legendary physicist John Archibald Wheeler put it, space-time tells matter how to move. Matter tells space-time how to curve. Think about that for a second. It's a cosmic conversation. Matter, with its mass and energy, tells space-time how to bend and warp. In return, that curved spacetime lays out the highways that matter must travel along. This isn't a stage where the universe performs. Spacetime is one of the lead actors. It's a dynamic, living thing, shaped by everything in it. So, what happens when we try our thought experiment? What happens when we take this 4D fabric and just rip out the three dimensions we call space? It's an act of cosmic vandalism that's hard to wrap your head around. We're not just getting rid of the empty space between planets. We are deleting the very ideas of location, distance, direction, size, and shape. Think about an electron. In our universe, an electron is a fundamental particle with properties we describe in space. It has a quantum wave function that tells us the probability of finding it at a certain location. It has a spin, which is tied to its angular momentum, a property that needs a direction in space to make sense. In a spaceless universe, all that is gone. Poof. An electron can't be at a point because there are no points. It can't have a size because size is a measure of spatial extent. It can't have spin because there's no up or down for it to orient to. Any quality that needs a spatial context is instantly and totally erased. Our entire universe, with its swirling galaxies, massive nebulae, and us, would be crushed down to a single, dimensionless something. You can't even call it a point, like we normally think of one, because a point is a location in space. This is a state of being with no geometry at all. This is the bleak starting point for our new reality. A universe without a where. All we have left is the relentless tick-tock of a clock, a pure sequence of before and after. So the big question is, in this dimensionless nothingness, what could possibly happen? What is there for time to even measure? The ghost in the singularity. So, what about matter? Could the basic building blocks of our reality exist in a universe with only time? In our world, the structure of everything is built on rules that are fundamentally spatial. Take the atom. It has a nucleus at its center, with electrons buzzing in specific orbitals around it. The very words we use, around, center, orbitals, are all about space. These concepts give atoms their structure, letting them bond into molecules, which then build everything from a grain of sand to the neural networks in your brain. In our spaceless universe, that whole system collapses. Let's just take two particles, say, two electrons. A bedrock rule of quantum mechanics, the Pauli exclusion principle, says that two identical fermions can't be in the same quantum state in the same place at the same time. It's the basic reason matter is stable and why you can't just walk through walls. It's what keeps atoms from smushing together. But in a universe with no space, location is meaningless. There's no same place for two electrons to avoid, and no different place for them to be. Every single particle in this universe would be crammed into the same dimensionless state. The Pauli exclusion principle would have no rules to enforce. Every proton, neutron, and electron in the universe would be forced into this single, non-spatial existence. The result is something that's hard to describe. You might want to call it a singularity, like the infinitely dense point inside a black hole. But even a singularity is a point asterisk in space. Our state is something much weirder. It's a universe's worth of matter with all its properties stripped away, existing as pure potential without any form. No structure means no atoms. No atoms, no molecules. No molecules, no stars, no planets, no chairs, and no people. The very definition of matter as an organized substance just dissolves. But what about the forces that hold matter together? Could they stick around? Think about the fundamental forces of nature. Electromagnetism, which governs light and how charged particles interact, depends on fields that travel through space. The strength of this force drops off with the square of the distance. But if there's no distance, how can the force work? A photon, the particle that carries the electromagnetic force, is a wave that travels at the speed of light. But speed is just distance divided by time. Without distance, the concept of speed is gibberish. The strong and weak nuclear forces, which hold the nucleus of an atom together, are also defined by their range, how far their influence extends over a certain spatial distance. Without that distance, their very definitions are toast. And gravity? General relativity tells us gravity isn't a force but the curvature of spacetime itself. If you get rid of space, you get rid of the very thing that's being curved. The entire machine of gravity just stops working. Even the most famous equation in all of physics, E equals mc squared, becomes meaningless. E is energy, m is mass, and c is the speed of light. We've already seen that the speed of light, a measure of distance over time, is now an undefined concept. Mass, as a structured property of matter, has also dissolved into our dimensionless goo. Without a working definition of mass or the speed of light, the equation that ties them together loses its power. So, in our attempt to build a universe of pure time, we've already lost everything. No matter, no structure, no forces, no energy as we know it. We're left with a void. Not an empty space, but a void of the very idea of space. But we're not done. Because even in this absolute nothingness, we have one thing left: a sequence of events. A before and an after. The question now becomes much, much more abstract. Could something non-physical exist? Could a single thought just flicker into being? I think, therefore I am. Not? This might be the most profound question our thought experiment can ask. If you were reduced to a purely non-physical being in this spaceless void, could you think? Let's ground this in what we actually know about thought. As far as science can tell, a thought isn't some ghostly whisper. It is a physical process. Your consciousness, your memories, your feelings, they all emerge from the incredibly complex dance of around 86 billion neurons in your brain. Each thought you have is a specific pattern of electrochemical signals firing between these neurons. A memory isn't stored in one spot. It's a pattern of connections strengthened across a huge network of cells. When you remember something, you're reactivating that specific spatial and temporal pattern. A signal literally travels down the axon of one neuron, jumps a physical gap called a synapse, and triggers a response in the next one. The key word here is travels. That process takes time, but it also, critically, covers a distance. The very architecture of your brain is spatial. Different areas of the brain do different jobs. Your visual cortex, at the back of your head, processes info from your eyes. Broca's area, in the frontal lobe, is key for producing language. The hippocampus, tucked deep in the temporal lobe, is essential for making new memories. The whole system is a masterpiece of spatial organization. The speed these signals travel, up to 120 meters per second, is perfectly tuned to allow for the complex processing that we call consciousness. Now, let's go back to our universe of pure time. We've already figured out that physical structures can't exist. There's no brain. No neurons, no axons, no synapses. There is no physical space for a signal to travel across. The entire biological machine that we understand as the basis of thought is gone. So, could a thought exist in a purely abstract, non-physical form? Let's imagine a disembodied consciousness. What would it even think about? All of our concepts are learned from and grounded in a world of space. We think in deeply spatial metaphors. A heavy topic, a close relationship, a high ideal, a deep thought. Even our most abstract ideas, like math, often lean on spatial intuition. We picture graphs, geometric shapes, and number lines. A consciousness in a spaceless universe would have zero sensory input. No sight, no sound, no touch. It would have no body. It would have no external world to see or touch. It wouldn't even have a memory of such a world, because the physical hardware to store that memory never existed. Could it think of itself? The philosopher René Descartes famously said, "I think, therefore I am." But his I was a thing that could perceive, doubt, and understand all processes tied to a physical brain in a physical world. In our scenario, the I has no properties. No size, no shape, no location, no past. What is there to be self-aware of? The self, in many ways, is a story we build from a lifetime of experiences. But experiences require interaction. They require a difference between self and other, between the observer and the observed. In a dimensionless state, that separation is impossible. We're forced into a startling conclusion. Just as matter and energy need space to be defined, so does thought. Consciousness, as far as we can scientifically describe it, isn't a property of a single point. It's an emergent phenomenon that arises from the complex, spatially organized interaction of many smaller parts. Without space, you don't just lose the brain's hardware. You lose the basic logic that the software of consciousness runs on. We're left with a universe that has a sequence, a progression from one moment to the next, but with nothing to change, nothing to act on, and nothing to be aware of the change. We have a clock ticking in an empty room, where the room itself doesn't exist. This leads us to our final, biggest question. What is this ticking clock, this flow of time, actually doing? What is causality in a universe where nothing can cause anything else? The unbroken chain of nothing. We've reached the last refuge of our thought experiment. We've thrown out space, and with it, we've watched matter, energy, and even the possibility of thought itself dissolve into nothing. All we have left is the pure, abstract idea of time. A relentless march from before to after. This is the home of causality, the most basic law of the cosmos. Event A happens, which causes event B, which causes event C. This chain of cause and effect is what gives time its direction, its arrow. It's why we remember the past but not the future. The second law of thermodynamics gives us a physical reason for this. In any closed system, entropy, a measure of disorder, always increases. Eggs break but they don't unbreak. Ice melts but doesn't spontaneously freeze itself solid again. This march toward higher entropy is the engine of time's arrow. But in our spaceless universe, what does any of that mean? Entropy is a statistical property of a system with many parts. It's about how particles are arranged. The more possible arrangements a system can have, the higher its entropy. An unbroken egg has low entropy because all its molecules are in a very specific, ordered arrangement. A broken egg has high entropy because its molecules are splattered in one of a gazillion disordered arrangements. In a dimensionless state, there are no parts to arrange. There is only one possible state. The state of being a dimensionless state. There can be no increase in disorder, because there was no order to begin with. The second law of thermodynamics, the very engine that gives time its direction, has nothing to work on. So, we have a sequence of moments t1, t2, t3, but the state of the universe at each moment is identical. Nothing changes. The universe at time t1 is a dimensionless something. The universe at time t2 is the exact same dimensionless something. This creates a massive paradox. Does time have any meaning if it isn't measuring change? The philosopher Aristotle argued that time was a measure of change or motion. For him, a universe without change would be a universe without time. Many modern physicists would agree, saying time is what a clock measures, and a clock is always a physical process, a swinging pendulum, a vibrating crystal, the decay of an atom. In a universe with no physical processes, there can be no clocks. From this point of view, our whole experiment, a universe with time but no space, just collapsed in on itself. By getting rid of space, we accidentally got rid of the very things, change, process, causality, that give time its meaning. But maybe that's thinking about it the wrong way. Let's push one step deeper. Let's just assume time is more fundamental than that. What if the universe could just exist as a sequence of abstract states? State 1, then state 2, then state 3. Pure information, changing over time. Could that work? This is where our thought experiment runs headfirst into the wall of modern physics. Because the last century of research has revealed a truth that is both stranger and more beautiful. Time isn't the master clock of the universe. In fact, it might not be fundamental at all. And the reason for this brings us right back to the very thing we tried to throw away: space. The space-time weave. This whole time, we've been treating space and time like two things we could pull apart. But Einstein's theory of special relativity shows us that's impossible, and it all boils down to one cosmic speed limit: the speed of light. One of the core ideas of relativity is that the speed of light in a vacuum is the same for every single observer, no matter how fast they're moving. This simple rule has some seriously weird consequences. It means that people moving at different speeds will actually experience time and measure distances differently. An astronaut on a super-fast spaceship will experience time passing more slowly than someone on Earth. That's time dilation. They'll also measure distances in their direction of travel as being shorter. That's length contraction. So, time and space are flexible. They stretch and shrink depending on how you're moving. This might make it sound like they're separate things you can squish and pull independently. But Einstein, along with his former teacher Hermann Minkowski, found something amazing. While space and time are relative, they're connected in a very specific way. There's a single value, a combination of both space and time, that stays the same for everyone. This is called the asterisk spacetime interval. Imagine two events: a firecracker going off right here, right now, and another 100 meters away, 1 second from now. Different people, moving at different speeds, will disagree on the distance in space and the time between those two explosions. But when they each plug their own measurements of space and time into the formula for the spacetime interval, they will all get the exact same number. This is a revolutionary idea. It means reality isn't a 3D space plus a 1D time. Reality is a unified 4D spacetime. The spacetime interval is the asterisk true distance in this 4D reality, and it is absolute. This structure directly impacts cause and effect. For any event, we can draw a light cone. This cone shows all the possible futures that can be influenced by that event, limited by the speed of light. Anything outside that cone is in the elsewhere. It can't be affected by the event, and it can't affect the event, because to do so, information would have to travel faster than light. So what happens to the space-time interval and the light cone in our spaceless universe? The formula for the space-time interval literally combines spatial distance and time. If you set the spatial distance to 0, the equation falls apart. It's no longer describing a relationship between two things. It's just a statement about one. The core idea of an invariant interval, the bedrock of relativity, vanishes. The light cone, which defines the borders of causality, also collapses. A light cone has a width in space. Without space, the cone has no width. It becomes an infinitely thin line. The future is no longer a huge volume of potential places, but a single, predetermined path. This is the ultimate reason our premise fails, at least according to relativity. Space and time are not two separate items on a cosmic menu that we can pick and choose from. They are two aspects of a single, deeper reality. Asking for time without space is like asking for the North Pole of a magnet without a South Pole. The properties of one are defined by its relationship with the other. You can't tear the weave apart, because there's no weave. There's only a single, unified fabric. Trying to remove space from space-time is a fatal operation. But the story doesn't end there. In the last few decades, an even more radical idea has come out of the bizarre world of quantum mechanics. It suggests that not only are space and time inseparable, but they might not be fundamental at all. They could be emergent illusions, bubbling up from a much stranger reality. The ultimate twist: time as an illusion. Our journey started with a simple question, but it's led us to the very edge of known physics, the hunt for a theory of quantum gravity. This is the attempt to unite Einstein's general relativity, our theory of the very big, with quantum mechanics, our theory of the very small. And it's here that the idea of time faces its biggest challenge yet. In the 1960s, Physicists John Wheeler and Bryce DeWitt tried to smash these two theories together into one master equation. The result, known as the Wheeler-DeWitt equation, was meant to describe the quantum state of the entire universe. But it had a shocking surprise inside. The variable for time was completely missing. According to a literal reading of the equation, the universe as a whole is static and timeless. The quantum wave function of the universe doesn't evolve. It just is. Past, present, and future might all exist at once in a single, unchanging, block universe, just like all points in space exist at once. Our feeling of time flowing, in this view, could be a deep and profound illusion. This is famously known as the problem of time in physics. If time isn't fundamental, if it vanishes from our most basic description of reality, then where does our powerful, undeniable experience of its passage come from? A mind-bending new theory offers an answer. Time isn't a fundamental feature of the universe, but an emergent one. It's like temperature. A single water molecule doesn't have a temperature. Temperature is an average property that emerges from the jiggling of countless molecules. You won't find temperature in any single part, but it appears from the sum of the whole. In the same way, some physicists are now exploring the idea that time itself emerges from a purely quantum phenomenon, entanglement. Entanglement is one of the weirdest and most powerful ideas in science. It describes a deep link that can form between two or more quantum particles. Once entangled, these particles act like a single system, no matter how far apart they are. If you measure a property of one particle, you instantly know the same property of its partner, even if it's on the other side of the galaxy. Einstein famously called this spooky action at a distance. The new theory flips our whole perspective. What if the universe, at its most fundamental level, is just a giant network of these quantum entanglements? Some theorists propose that the evolution of these entanglement networks is what we perceive as the flow of time. The ticking of the universal clock is nothing more than the constant shifting and growing of quantum connections. One of the most radical ways to put this is, entanglement doesn't happen in spacetime. Entanglement creates spacetime. Think about that. Space isn't a pre-existing box. It's a geometric picture of the entanglement structure of the whole system. The more entangled two particles are, the closer they are in the emergent space. And time is the process of these entanglement patterns changing and getting more complex. This gives us the final, devastating answer to our original question. What if time existed but space did not? If space is the map of quantum entanglement, and time is the measure of how that map evolves, then the two are born from the exact same quantum source. You can't have one without the other, because they are two sides of the same coin. If you remove space, you're not just deleting a dimension. You are erasing the entire network of quantum connections that defines reality's structure. And if you erase that network, you also erase the dynamic process of its evolution. You erase time itself. Our thought experiment was to see what would happen in a universe with only time. The ultimate answer, coming from the farthest frontiers of physics, is that such a universe isn't just empty. It's impossible. The echo in the void. We started this journey with a simple act of deletion. We took our reality, this rich, four-dimensional spacetime, and we tried to erase space. We thought we'd be left with a pure, unfiltered flow of time, a universe of just before and after. What we found was a cascade of annihilation. Without space, matter lost its structure and dissolved into a featureless, dimensionless soup. The fundamental forces had no distance to act across. Energy lost its meaning. The physical architecture of the brain vanished, and with it, any scientific basis for thought or consciousness. Even the arrow of time, powered by the endless march of entropy, ground to a halt. In a universe with no parts to rearrange, there can be no change, no disorder, and therefore, no direction for time to flow. At every single step, our attempt to isolate time proved to be a catastrophe. But the final revelation was the most profound. We learned that the relationship between space and time isn't just one of dependence. It's one of a shared identity. From Einstein's view, they are fused into a single spacetime fabric, where the true distance between events is a mix of both. From the even more modern perspective of quantum gravity, both space and time might be illusions, emergent properties of a deeper quantum reality. They may be two different products of quantum entanglement, with space being the map of those connections and time being the story of how they change. Our thought experiment failed. It failed because it was based on a false assumption that space is just a cosmic container we could choose to get rid of. What we've learned is that space is not a container. It's woven into the very definition of existence, causality, matter, and even time itself. We asked what would exist in a universe with only time. The answer, it seems, is nothing. Not even time itself. But that failure is the whole point. It teaches us something vital about our own universe. The fact that you are here, that you can think, that you can see a universe filled with incredible structure and a reliable flow of cause and effect, is a direct consequence of the unbreakable bond between space and time. They are the twin pillars holding up all of reality. This trip into a spaceless void forces us to ask what is truly fundamental. We've seen that time, as we know it, can't exist without space. But that leaves us with one last, massive question. If a universe without space is impossible, does that mean space is the most fundamental thing? Or is it something even deeper, that hidden, quantum network of entanglement from which both space and time might spring? What do you believe is at the very bottom of it all? Let us know what you think in the comments. We read as many as we can, and your ideas really do help shape the conversations we have here. If you enjoy wrestling with these huge questions about the nature of reality, make sure to subscribe and turn on notifications so you don't miss our next journey into the unknown. And while you wait, you might enjoy our video on whether the universe could have more than one dimension of time. Einstein's mind-bending secret that unlocks reality. All your life, you've taken one thing for granted. That time marches forward at the same steady pace for everyone. You probably think that 1 second on your watch is 1 second on a watch in Tokyo, and 1 second on a satellite zipping around Jupiter. But what if that's all wrong? What if the most fundamental thing you think you know about reality, that steady, river-like flow of time, is just an illusion? What if moving fast didn't just change where you are, but actually slowed down your personal experience of time itself? This isn't just a wild theory. It's a fundamental secret of our universe. It's a clue that reveals space and time are two sides of the same coin, a single fabric holding our reality together. So, we're going to spend some time together dismantling your perception of reality and rebuilding it from the ground up, using one of the most elegant and revolutionary ideas in human history. By the end of this, you won't just understand Einstein's secret. You'll start to see the universe through his eyes. The world before Einstein, a clockwork universe. Before we can really appreciate the beautiful chaos Einstein unleashed, we have to get a picture of the world he was born into. For over 200 years, physics was dominated by one towering figure, Sir Isaac Newton. Newton gave us a version of the universe that was comforting, made sense, and, for all practical purposes, seemed perfect. Think of the universe as a giant, infinite stage. This is what Newton called absolute space. It's a rigid, unchanging, three-dimensional grid. Every object has a precise address on this grid in x, y, and z coordinate. It's the backdrop for all the cosmic drama, but it never actually gets involved. It's just there. Passive, eternal, and absolute. Now, imagine a single, cosmic clock, hidden somewhere, ticking away with perfect, unshakable rhythm. This was Newton's absolute time. Every tick of this universal clock happens for everyone, everywhere, at the exact same instant. Whether you're on Earth, Mars, or in a distant galaxy, now is the same for all of you. Time flows like a great, unchangeable river, sweeping everything along at the same rate. It's a simple, elegant idea, and it fits our daily experience almost perfectly. If I snap my fingers, it feels like that. Now is the same now for you, wherever you are. My now is your now. In this Newtonian world, motion was also beautifully straightforward. Say you're on a train moving at 50 kilometers per hour, and you throw a ball down the aisle at 10 kilometers per hour. For someone standing on the platform, the ball's speed is simple addition. 50 plus 10 equals 60 kilometers per hour. This is called Galilean relativity, and it's basically the physics of common sense. Speeds just add up. This clockwork universe was a masterpiece of predictability. With Newton's laws, you could calculate the orbit of a planet or the path of a cannonball. The universe was a grand, deterministic machine. If you knew where every particle was and where it was going, you could, in theory, predict the entire future. There was a deep comfort in this. The rules were fixed, space was the stage, and time was the impartial judge, marching on at the same pace for everyone and everything. For this whole system to work, there was a hidden assumption that there was no ultimate speed limit. Information, it seemed, could travel instantly. Under this view, if the sun were to suddenly vanish, the Earth would instantly fly out of its orbit, feeling the gravitational change at that exact moment. Gravity was seen as a force that acted across vast distances in no time at all. This was the tidy, predictable world of physics. It worked so well that questioning it seemed ridiculous. But near the end of the 19th century, a crack started to appear in this perfect facade. And it all started with the most ordinary thing in the universe: a simple beam of light. The crack in reality, a stubborn beam of light. The story of modern reality begins not with a bang, but with a few equations. In the 1860s, the brilliant Scottish physicist James Clerk Maxwell was working to unify the separate laws of electricity and magnetism. In doing so, he cooked up 4 of the most famous equations in all of physics. And buried inside them was a startling prediction. Maxwell's equations showed that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric one. They could feed each other, creating a self-propagating wave of energy, an electromagnetic wave. When Maxwell calculated the speed of these waves, he got a number that was shockingly familiar. About 300,000 kilometers per second. This was the known speed of light. It was a huge discovery. Light itself was a wave of electricity and magnetism. But this breakthrough came with a seriously nagging puzzle. The equations gave us the speed of light, see but they didn't say what this speed was relative to. Think back to our train. The speed of the ball only made sense if we knew who was measuring it, the person on the train or the person on the platform. But Maxwell's equations just said, "c." It didn't seem to care if the source or the observer was moving. This was just bizarre. Physics always dealt with relative speeds. An absolute speed, with no point of reference, felt meaningless. To solve this, 19th century physicists brought back an old idea: the luminiferous ether. They proposed that all of space was filled with this mysterious, invisible substance. The ether, they figured, was the stationary medium that light traveled through, just like sound travels through air. So, the speed of light, see was its speed relative to the ether. This seemed to fix things. The absolute speed in the equations now had a reference. And it led to a testable prediction. The Earth, orbiting the Sun, has to be moving through this ether. So, we should be able to feel an ether wind, just like you feel a breeze when you stick your hand out of a moving car window. If we measured the speed of light moving in the same direction as Earth, it should seem a bit slower. If we measured it at a right angle, it should be unaffected. This is exactly what two American scientists, Albert Michelson and Edward Morley, set out to test in 1887. They designed an incredibly sensitive instrument called an interferometer. It split a beam of light in two, sent them on perpendicular paths, and then brought them back together. If one beam was slowed by the ether wind more than the other, the waves would be out of sync when they recombined, creating a telltale pattern. The experiment was a marvel of precision. They floated the whole thing on a pool of mercury for smooth rotation. Michelson and Morley fully expected to see that pattern shift as they rotated the device. They ran the experiment. They rotated it. They checked their results. And they found absolutely nothing. No shift. No change. The speed of light was exactly the same, no matter which way they pointed their machine. It was as if there was no ether wind at all. This was a crisis. One of the most famous, failed, experiments in history. Maybe the Earth was dragging the ether along with it? Nope, other astronomical observations ruled that out. They tried again at different times of the year, when the Earth was moving in a different direction. Same result. Nothing. The implications were shattering. The experiment seemed to prove two contradictory things. First, the laws of motion said the Earth had to be moving. Second, the experiment showed the speed of light * wasn't changing because of that motion. Let's go back to the train to feel how absurd this is. The train is speeding along. Someone on the train shines a flashlight forward. They measure the light's speed and get (C). But you, standing on the platform, also measure the speed of that very same beam of light. Common sense says you should get (C) plus the train's speed. But you don't. You get exactly (C). Someone on another train going the opposite direction also measures it as (C). Everyone, everywhere, no matter how they're moving, measures the speed of light to be the exact same. This was the crack in the foundation of physics. It broke the simple rules of adding speeds. It defied all logic. The two pillars of classical physics, Newton's laws of motion and Maxwell's laws of electromagnetism, seemed to be in a head-on collision. Physics was broken. The universe was presenting a riddle that seemed impossible to solve. How can the speed of light be the same for someone moving and someone standing still? The answer wouldn't come from some famous professor, but from a young, unknown patent clerk in Switzerland, who was about to have a very, very good year. The young rebel's dream, Einstein's audacious leap. In 1905, Albert Einstein wasn't the icon we know today. He was a 26-year-old patent examiner who'd been a rebellious student and struggled to find an academic job. But while he spent his days looking at other people's inventions, he spent his nights wrestling with the biggest problems in physics. The paradox of light's constant speed obsessed him. He'd been kicking it around in his head for years. As a teenager, he famously wondered what it would be like to ride alongside a beam of light. If you could match its speed, shouldn't the light wave look frozen to you? But Maxwell's equations said these waves must always move at (C). A frozen light wave didn't seem possible. While other great physicists were trying to patch up the old theories to explain the Michelson-Morley result, Einstein took a much bolder approach. His genius wasn't in adding complexity, it was in embracing simplicity. He decided to start fresh, with just two basic ideas, or postulates. First was the principle of relativity. This idea actually went back to Galileo and said that the laws of physics should be the same for anyone moving at a constant speed. It's why on a smooth flight, if you close the window shades, you can't do any experiment that would prove you're moving. His second postulate was the wild one. He took the bizarre result from the Michelson-Morley experiment and declared it a law of the universe. The speed of light in a vacuum is the same for all observers, no matter how they're moving. Einstein didn't try to explain why it was constant. He just said, let's assume it is, and see what the consequences are. He decided to trust the experiment more than he trusted centuries of common sense. He asked a revolutionary question. If these two things are true, what do we have to throw out? If the speed of light refuses to change, what else in the universe has to be flexible? His answer was the very foundation of Newton's world: absolute space and absolute time. Einstein realized that if the speed of light is the same for everyone, then our measurements of distance and time can't be. They have to be relative. Space must be able to shrink, and time must be able to stretch, or slow down. The universe, he proposed, has a cosmic speed limit that nothing can break, and it literally bends its own rules of space and time to make sure that limit is always enforced. In his 1905 paper, on the electrodynamics of moving bodies, Einstein laid out this new reality, which became known as the theory of special relativity. It was special because it only dealt with steady, non-accelerating motion. He'd spend the next 10 years working on a general theory that included gravity. But even this special theory was enough to turn physics completely upside down. He had solved the riddle of light, and in doing so, he had uncovered an even deeper secret about how reality itself works. The secret ingredient of reality: unveiling spacetime. So, Einstein's big idea was that our measurements of space and time had to be flexible. But how does that actually work? How can two people experience time differently? The secret, the truly mind-bending core of it all, is that space and time aren't separate things. They're woven together into a single, four-dimensional fabric: spacetime. That's a weird concept, so let's build it up. We're used to thinking in three spatial dimensions: length, width, and height. But to describe an asterisk event, you need a fourth piece of information: when it happens. To meet a friend, you need a location, 3 space coordinates, and a time, 1 time coordinate. So in a way, we've always lived in 4 dimensions. But before Einstein, space was the stage and time was the clock, totally separate. What Einstein and his former teacher Hermann Minkowski realized was that this was the wrong way to see it. Spacetime isn't just a list of 4 coordinates. It's a real, geometric thing. And here's the most profound insight. Everything in the universe is always moving through spacetime at one single, constant speed. The speed of light. Asterisk. That's the sentence that unlocks everything. Let it sink in. Right now, as you sit there, seemingly perfectly still, you are traveling through spacetime at the speed of light. How can that be? Well, right now, most of your motion is through the time dimension. When you're sitting still, you're using your entire speed budget to travel into the future at the maximum possible rate. But what happens when you start moving through space? When you get up and walk, you divert some of your motion from the time dimension into the space dimensions. You have a fixed budget of speed through spacetime. See. The more of that budget you use to move through space, the less you have left over to move through time. This means the faster you move through space, the slower you move through time relative to someone who's standing still. This is the origin of asterisk time dilation. It's not a trick. Your personal, biological clock literally slows down. Still feels a bit abstract, right? Let's make it concrete with Einstein's favorite tool, a thought experiment. This is the famous asterisk light clock asterisk, and it's the best way to get that aha moment. Imagine a clock made of 2 mirrors, with a single photon of light bouncing between them. Each time the photon hits the top mirror and returns, the clock ticks. First, let's say you're holding the clock. From your point of view, the photon just goes straight up and straight down. It travels a certain distance, let's call it d. The time for one tick is simple. Time equals distance, speed. So, one tick takes c seconds. Easy enough. Now for the magic. Let's put that same clock on a transparent spaceship flying past you at, say, 80% of the speed of light. From your perspective on a space station, what do you see? Well, the clock is moving. The photon leaves the bottom mirror, but while it's traveling up, the whole clock moves to the right. To hit the top mirror, the photon has to travel on a longer, diagonal path. Then, on its way back down, the clock moves even more, so the photon has to travel another long, diagonal path to catch up to the bottom mirror. Here's the knockout punch. From your stationary viewpoint, the photon in the moving clock traveled a much greater distance than the photon in your own clock. It took 2 long diagonal trips instead of 1 short vertical one. And now, remember Einstein's second rule. The speed of light is the same for everyone. You, on the station, have to measure the speed of that moving photon to be exactly see . So, we have a photon that traveled a longer distance but at the exact same speed. What does that mean? If speed equals distance, time, and the speed is constant while the distance is longer, then the time for one tick must also be longer. From your perspective, the moving clock is ticking slower than yours. And it's not the clock that's broken. It's time itself that has slowed down for the spaceship. The astronaut on board is aging more slowly than you are. Their heart is beating more slowly. All relative to you. From the astronaut's perspective, of course, their clock is ticking normally. It's your clock on the station that looks like it's ticking slowly. This is relativity. All viewpoints are equally valid. This isn't just a weird time thing. It's paired with another effect called length contraction. To keep the speed of light constant, space itself must shrink in the direction of motion. To the astronaut on that ship, the distance to their destination actually seems shorter than it does to you. So, this is Einstein's secret. The universe isn't a static stage with a universal clock. It's a dynamic, 4D spacetime fabric. We're all swimming through it at the speed of light. When we move through space, we're just trading some of our speed through time for speed through space. They are locked in a dance, stretching and shrinking to protect the one true constant, the speed of light. The universe wakes up, consequences of the new reality. This all brings us back to our shocking hook. The reason moving fast slows your personal time is because you're trading motion through time for motion through space. And this isn't just a mind game. It's the physical reality we live in, with real, measurable consequences. The most practical example might be in your car or your pocket right now. GPS. Your GPS receiver figures out where you are by talking to satellites orbiting the Earth. It needs to know the exact time signals are sent and received, requiring the clocks on the satellites and on the ground to be perfectly in sync. But there are 2 problems. First, the satellites are moving fast, about 14,000 kilometers per hour. Special relativity says their clocks should tick slower than ours by about 7 microseconds every day. But there's a second, bigger effect from Einstein's general relativity. The satellites are in weaker gravity, which actually makes their clocks tick faster by about 45 microseconds a day. Do the math, and the net result is that the satellite clocks run ahead of clocks on Earth by about 38 microseconds, 38,000 nanoseconds, every single day. It's not much, but if engineers didn't correct for it, your GPS would be off by about 10 kilometers every day, making it totally useless. The fact that you can navigate to a coffee shop is daily proof that time itself runs at different rates depending on your speed and gravity. Another beautiful piece of evidence comes from the sky. Our upper atmosphere is constantly being hit by high-energy cosmic rays, which create a shower of short-lived particles. One of these is called a muon. Muons are like heavy, unstable electrons. In a lab, a muon at rest only lives for about 2 microseconds, that's just over 2 millionths of a second. These muons are created about 10 kilometers up and travel towards the ground at nearly the speed of light, around 99.5% of it. Now, let's do the old-school math. Even at that insane speed, in its 2 microsecond lifetime, a muon should only travel about 660 meters. It shouldn't even come close to reaching the Earth's surface. We should barely detect any of them down here. And yet, we do. We detect a whole bunch of them at sea level. How? Time dilation. From our perspective, the muon is moving so fast that its internal clock is ticking much slower than ours. At 99.5% the speed of light, its time is stretched by a factor of about 10. So, from our point of view, its lifetime isn't 2 microseconds. It's more like 22 microseconds. In that extended lifetime, it has more than enough time to travel the 10 kilometers and reach our detectors. The muon literally survives its own death sentence because its high-speed journey slowed down its personal experience of time. And of course, we have to talk about the asterisk twin paradox. Imagine two twins. One stays on Earth, and the other takes a rocket to a nearby star at nearly the speed of light, turns around, and comes back. When the traveling twin returns, they will be younger than the twin who stayed home. This seems like a paradox because, from the traveling twin's view, didn't the Earth move away and come back? Shouldn't the Earth-bound twin be younger? The solution is that their trips weren't symmetrical. The traveling twin had to accelerate, slam on the brakes, turn around, and accelerate again. They changed their frame of reference. It's the twin who does the accelerating that experiences less time. When they reunite, the space-faring twin is biologically younger. It's not a paradox, just the weird but consistent logic of spacetime. Finally, the most famous equation of all, E=mc², is a direct consequence of all this. Einstein showed that mass and energy are two sides of the same coin. As you try to push an object closer and closer to the speed of light, its effective mass increases, making it harder and harder to accelerate further. It would take an infinite amount of energy to get any object with mass to actually hit the speed of light. The cosmic speed limit is woven into the very fabric of mass and energy. The world Einstein showed us isn't the common-sense world we think we live in. It's a world where time and space are fluid, where reality depends on how you're moving, and a world that's proven true every time you ask your phone for directions. The plot thickens. Einstein's second masterpiece. But Einstein knew his 1905 theory wasn't the whole story. It was beautiful, but it had a glaring hole. It perfectly described space and time for things moving at a constant speed, but it said nothing about acceleration. And more importantly, it said nothing about the most powerful force in the cosmos, gravity. Newton's view of gravity, an invisible, instantaneous force, was completely at odds with special relativity's cosmic speed limit. If nothing can travel faster than light, how could gravity act instantly across the solar system? Einstein realized the secret of spacetime was even deeper than he'd first thought. His journey wasn't over. The special theory had united space and time. His next great challenge would be to unite spacetime with gravity itself. And that would take another 10 years of grueling work, leading to his second masterpiece, the general theory of relativity, and an even wilder vision of reality. If this journey into the fabric of reality has stretched your mind, and you want to explore more of the universe with us, do us a favor and subscribe to the channel. Click the little bell icon, too, so you don't miss what's coming next. We have so much more of the cosmos to unpack together. For centuries, we saw the universe as a bunch of objects moving through empty space, all ruled by one giant, ticking clock. But a stubborn beam of light that refused to play by the rules forced a young patent clerk to tear that entire picture down. Space and time aren't the background for the show. They're not even separate. They're a single, dynamic fabric called spacetime. Our journey through it is far more personal and flexible than we ever imagined. That was Einstein's secret. He revealed a universe where each of us travels on our own unique path through both space and time, a universe where your reality is fundamentally shaped by your motion. The next time you're on a train, a plane, or even just walking down the street, remember, you are, in a very real sense, a time traveler. And you are seeing just one slice of a much grander, four-dimensional reality.